In this very moment, as you read these words, you are traveling through time at the speed of light, surfing on waves of space-time that ripple outward from every atom in your body. You might think you're sitting still, anchored in a familiar room, experiencing the steady tick of seconds passing by. But what if everything you believe about space and time, these most basic ingredients of your reality, is nothing more than a beautiful illusion? What if the stage upon which your entire life unfolds doesn't actually exist the way you think it does? Today, we're going to unravel the deepest mystery in all of science. What are space and time actually? Join me as we journey from the comfortable lies of our everyday experience to the mind-bending truths that modern physics has revealed. Truths so strange, they make science fiction seem mundane, so profound, they challenge the very meaning of existence itself. Before we dive in, let me know what corner of space-time you're occupying right now. Drop your location and local time in the comments below. I love knowing that we're all sharing this moment together, scattered across the globe, but united in our curiosity about the cosmos. Step outside on a clear night and look up at the stars. What do you see? Points of light scattered across a vast black dome, a cosmic theater where celestial actors perform their eternal dance. The moon glides smoothly across this backdrop. Planets wander among the constellations, and if you're lucky, a meteor might streak across the sky like a cosmic brushstroke. This is the universe your senses present to you, a three-dimensional stage upon which events unfold in orderly sequence. Space appears as an empty container, a vast box that holds everything from galaxies to grains of sand. Time flows like a river, carrying you inexorably from past to future, marking its passage with the steady rhythm of your heartbeat, the turning of seasons, the aging of your face in the mirror. But here's the thing about this cosmic theater. It's the most convincing magic trick ever performed. Your brain, that 3-pound universe of neurons, has evolved over millions of years to create this seamless experience of reality. It takes the chaotic flood of sensory data, photons hitting your retina, air molecules vibrating against your eardrums, chemicals binding to receptors in your nose, and weaves them into a coherent story of space and time. Consider this moment. You feel like you're experiencing now, a singular instant that separates the fixed past from the uncertain future. But neuroscience reveals that your now is actually a construction, a 2-3 second window where your brain integrates information from different senses that arrive at slightly different times. The light from these words reaches your eyes faster than the sound of your own breathing reaches your ears, yet your brain synchronizes them into a single unified present moment. Even more revealing is how your brain handles space. When you reach for a coffee cup, your brain doesn't just process where the cup is, it predicts where it will be by the time your hand arrives. It's constantly running simulations, building models, creating the experience of a stable, predictable spatial world from what is actually a torrent of incomplete and often contradictory information. This evolutionary magic show works beautifully for navigating everyday life. If you're a gazelle on the African savanna, you don't need to understand the relativistic effects of high-speed motion. You just need to run faster than the lion. If you're gathering berries, you don't need to contemplate the quantum nature of matter. You just need to distinguish ripe from unripe. But evolution optimized our brains for survival, not for truth. And the universe we actually inhabit is far stranger than anything our African savanna ancestors could have imagined. The ancient Greeks suspected this. They wondered if you could travel to the edge of the universe and stick your hand through, what would you find? If time is like a river, what are its banks made of? These questions seemed almost childish then, the kind of thing philosophers debated while practical people got on with living. They had no idea they were asking the most profound questions possible. Modern physics has revealed that our everyday experience of space and time is like watching shadows on a cave wall. We're seeing projections of a deeper reality that operates by rules so foreign to our intuition that even trained physicists struggle to accept them. The universe doesn't care about our evolutionary limitations. It operates according to principles that seem designed to confound every assumption we make about reality. Space isn't empty. It's teeming with energy and virtual particles. Time doesn't flow. It's more like a landscape where all moments exist simultaneously, and the boundary between space and time, it doesn't exist. They're aspects of a single unified entity that can bend, stretch, ripple, and even tear. We're about to pull back the curtain on the greatest show in the universe and discover that we've been both the audience and the magicians all along. The first crack in humanity's confident understanding of space and time appeared in 1887 in a basement laboratory in Cleveland, Ohio. Two physicists, Albert Michelson and Edward Morley, were trying to measure something that everyone knew had to exist: the luminiferous ether. Think of it this way. If you're on a moving train and you throw a ball forward, the ball's speed is your throwing speed plus the train's speed. This is basic physics, the kind you learn in elementary school. Light, everyone reasoned, must work the same way. Since light is a wave, it must travel through some medium, just like sound waves travel through air or water waves travel through water. As Earth orbited the sun, it should have been moving through this ether like a ship through water. Light traveling in the direction of Earth's motion should move faster relative to us, while light traveling perpendicular should move at a different speed. Michelson and Morley built an incredibly sensitive instrument to measure this difference. They found nothing, zero. The speed of light was exactly the same in all directions. This wasn't just puzzling, it was impossible. It violated everything physicists understood about motion, waves, and the nature of space itself. It was like discovering that no matter how fast you drive your car, your headlight beams always move away from you at exactly the same speed. The scientific community tried everything to explain away this result. Maybe Earth was dragging the ether along with it. Maybe the measuring equipment was flawed. Maybe there was some unknown force compressing their instruments. For 18 years, the physics world twisted itself into increasingly complex knots, trying to preserve their common-sense understanding of space and time. But other cracks were appearing. Maxwell's equations describing electromagnetism suggested that light should always travel at the same speed, regardless of the motion of its source. Perronet. Astronomers were noticing that the orbit of Mercury didn't quite match Newton's predictions. High-energy particles in cosmic rays seemed to live much longer than they should. Each anomaly was small, seemingly unrelated, but they were symptoms of something profound. Our intuitive understanding of reality was fundamentally wrong. The breakthrough came from an unlikely source, a 26-year-old patent clerk in Switzerland, who spent his days evaluating applications for electromagnetic devices, and his evenings pondering the deepest questions in physics. Albert Einstein had no access to sophisticated laboratories or prestigious academic positions. What he had was something more valuable: the audacity to question assumptions that everyone else took for granted. In 1905, Einstein published a paper with a deceptively simple title, On the Electrodynamics of Moving Bodies. In it, he made a proposal so radical that it would have seemed like madness if it hadn't explained everything. What if the speed of light is constant, not because there's some invisible medium carrying it, but because space and time themselves adjust to make it so? What if space contracts and time dilates when objects move at high speeds? What if simultaneity, the idea that two events can happen at the same time, is just another illusion created by our limited perspective? Einstein's special theory of relativity didn't just solve the puzzle of the Michelson-Morley experiment. It revealed that space and time were not separate, absolute entities, but aspects of a single malleable fabric. A fabric that responds to motion, that bends under the influence of gravity, that can carry waves of distortion across the cosmos. The implications were staggering. Time was no longer universal. A clock moving at high speed would run slower than a stationary one. Space was no longer fixed. Objects would literally contract in the direction of their motion. The future was no longer uncertain, while the past remained fixed. From the universe's perspective, all moments in time were equally real. Common sense had finally met its match, and this was just the beginning. Picture this: you're standing in a field, watching two lightning bolts strike simultaneously. One hits a tree to your left, Another hits a barn to your right. The flashes occur at exactly the same moment. You're certain of it. But now, imagine your friend is racing past you in a speeding car at the moment. The lightning strikes. From their perspective, the bolt that hit the barn happens first, then the bolt that hit the tree. Who's right? According to our everyday understanding, there should be one correct answer. Events either happen simultaneously or they don't. Time, after all, is time universal, absolute, the same for everyone, everywhere. Einstein's revelation was that you're both right. Simultaneity isn't a property of events themselves, but of the relationship between events and observers. There is no universal now stretching across the cosmos, no cosmic clockmaster ensuring that everyone experiences the same moment at the same time. Instead, space and time are woven together into what physicists call space-time, a four-dimensional fabric where the very concepts of when and where depend on who's asking the question. This wasn't just a minor correction to our understanding. It was a complete overthrow of reality as humans had conceived it for millennia. Since the dawn of consciousness, we had divided existence into two categories: space, where things are, and time, when things happen. Einstein revealed that this division was an artifact of our limited perspective, like insisting that left and right are fundamental properties of the universe, when they're really just descriptions relative to an observer. To understand how radical this was, imagine explaining color to someone who has only ever seen the world in black and white. You might describe red as warm or blue as cool, but until they actually see color, they can't truly grasp what you're talking about. Similarly, trying to understand space-time from our three-dimensional perspective is like trying to understand a sphere by only ever seeing its circular shadow. The mathematics of Einstein's theory revealed something even more profound. Space-time isn't just a passive stage where events unfold. It's a dynamic participant in the cosmic drama. Mass and energy don't just exist in space-time. They actively curve it, creating what we experience as gravity. John Wheeler, one of the great physicists of the 20th century, captured this beautifully. Space tells matter how to move. Matter tells space how to curve. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they'll follow curved paths around that depression. They're not being pulled by some mysterious force. They're simply following the straightest possible path through curved space. This is exactly how gravity works in Einstein's universe. The Earth doesn't pull the Moon toward it. Instead, the Earth's mass curves space-time, and the Moon follows the straightest possible path through that curved geometry. But Einstein's revolution went even deeper. His equations revealed that massive accelerating objects should create ripples in space-time itself, gravitational waves that travel at the speed of light, carrying information about the most violent events in the universe. For decades, these remained a theoretical prediction, a consequence of mathematics that seemed impossible to detect. Then, on September 14, 2015, at 5 a.m. Eastern Daylight Time, humanity heard space-time sing for the first time. The LIGO detectors in Louisiana and Washington simultaneously registered the infinitesimal stretching and compressing of space as gravitational waves from two colliding black holes washed over Earth. The signal lasted only a fifth of a second and changed the length of the LIGO arms by less than 1/10,000th the width of a proton. But it confirmed what Einstein had predicted a century earlier. Space-time is not empty, static void, but a dynamic medium that can carry information across the cosmos. The discovery of gravitational waves opened an entirely new window onto the universe. Just as we once thought the only way to study the cosmos was through visible light, then discovered radio waves, X-rays, and gamma rays, we now realize that space-time itself is a messenger, carrying news of cosmic events that no electromagnetic signal could reveal. But perhaps the most mind-bending consequence of Einstein's revolution is what it revealed about the nature of time itself. In our everyday experience, time has a clear direction. We remember the past, but not the future. Causes precede effects. Entropy increases. Yet Einstein's equations treat time as just another dimension, no more special than width, height, or depth. From the perspective of space-time, all moments, past, present, and future, exist with equal reality. This view, called the block universe, or eternalism, suggests that your birth, your death, and every moment in between are all equally real, like frames in a cosmic movie reel. The flow of time we experience is not a fundamental feature of reality, but an emergent property of consciousness, like the apparent motion of images in a film. Einstein himself found this deeply troubling. When his lifelong friend Michele Besso died, Einstein wrote to Besso's family, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Yet even he struggled to reconcile this timeless view of reality with the deeply human experience of loss, change, and becoming. The revolution Einstein sparked is still unfolding. Every day, physicists push deeper into the implications of his insights, discovering new ways that space and time violate our intuitions. We've learned that space can expand faster than the speed of light, that time can slow to a crawl near massive objects, that the quantum properties of particles can be instantaneously correlated across vast distances. Intropies of Uriendu-ser, the Auriendu-ser. Intropies of Uriendu-ser. Moindisi-Uriendu-ser. Intropies of Uriendu-ser. Moindisi-Uriendu-ser. 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 But we've also discovered that Einstein's revolution, as profound as it was, represents only the first act in an even grander drama. At the smallest scales of reality, where quantum mechanics reigns, space and time begin to lose their meaning entirely. And it's there, in the quantum realm, that our next chapter begins. Forget everything you think you know about empty space. Right now, in the seemingly vacant air between your eyes and this screen, space-time is alive with activity, more frenzied than the surface of a boiling pot. When physicists first began to understand Einstein's space-time, they often described it using the metaphor of a fabric, a cosmic sheet that could be stretched, compressed, and wrinkled by the presence of matter and energy. It's a useful analogy, but like all metaphors, it falls short of the stunning reality. Space-time isn't like fabric, it's more like a living ocean, constantly churning with waves, currents, and storms that we're only beginning to understand.
Yee. Yay. Yay. Yay.
At the largest scales, space-time is expanding, not into something. There is no outside for it to expand into, but expanding in the sense that the distance between galaxies is increasing everywhere, simultaneously. Imagine you're an ant on a balloon, and someone is inflating it. From your perspective, every other ant is moving away from you, but none of the ants are actually walking. The surface itself is stretching, creating new space between points. This expansion isn't uniform or peaceful. In some regions, space-time stretches smoothly, like a gentle tide. In others, it's turbulent and chaotic. Near black holes, space-time becomes a maelstrom, swirling and twisting so violently that it drags everything nearby into its dance. Physicists call this frame dragging, and it means that even the very definition of standing still becomes meaningless near these cosmic monsters. Imminence, near these cosmic monsters. But the true revelation of modern physics is that space-time doesn't just respond to matter and energy, it's made of something. At the quantum level, what we call empty space is actually a seething foam of virtual particles, constantly popping into existence and annihilating each other in timeframes so brief, they seem to mock our understanding of causality. These aren't just theoretical constructs, they have measurable effects. The Casimir effect, for instance, occurs when two metal plates, placed extremely close together in a vacuum experience a force pushing them together, created by the virtual particles in the space between them. Think of it this way. If you could zoom in on space-time with a microscope powerful enough to see down to the Planck scale, a distance so small that a proton is larger compared to it than a marble is compared to Earth, you wouldn't find smooth, continuous geometry. Instead, you'd discover a roiling quantum foam, where the very concepts of distance and duration become meaningless. At this scale, space-time itself is constantly being created and destroyed, winking in and out of existence in quantum fluctuations that happen trillions of times in every second. This quantum nature of space-time helps explain one of the most perplexing discoveries in modern cosmology: dark energy. Observations of distant supernovae revealed that the expansion of space-time is not slowing down, as gravity should cause it to, but actually accelerating. Something is pushing space-time apart with ever-increasing force, and we call this mysterious influence dark energy. But here's the puzzle. When physicists calculate how much energy the quantum foam of space-time should contribute to this expansion, they get a number that's larger than the observed value by a factor of 10 circumflex, 120. That's not a typo, it's 1 followed by 120 zeros, making it the worst prediction in the history of science. This suggests that either our understanding of quantum mechanics is catastrophically wrong, or there's some mechanism cancelling out almost all of the vacuum energy with impossible precision. The implications are staggering. We're living in a universe where the very fabric of reality is so finely tuned, all of the slightest change in the quantum properties of space-time would either cause the universe to collapse in on itself or expand so rapidly that atoms could never form. It's as if space-time is balanced on a knife's edge, held there by mechanisms we don't understand for reasons we can't fathom. Recent discoveries have made this picture even more complex. The detection of gravitational waves has revealed that space-time can ring like a bell, carrying acoustic signatures of cosmic collisions across billions of light-years. These waves stretch and compress space itself as they pass, meaning that the distance between any 2 points in the universe is constantly fluctuating by amounts too small to measure, but large enough to encode information about the most violent events in cosmic history. We've also learned that space-time has memory. When a gravitational wave passes through a region of space, it leaves behind a permanent displacement, a subtle change in the geometry that persists long after the wave has moved on. This gravitational memory effect means that space-time is not just a dynamic medium, but also a cosmic recording device, permanently marked by every significant event in the universe's history. Perhaps most remarkably, theoretical physicists are discovering that space-time might not be fundamental at all. Just as temperature emerges from the collective behavior of countless atoms, space-time might emerge from something more basic, quantum information perhaps, or the entanglement between fundamental particles. If this is true, then asking, what is space-time made of, might be like asking, what is temperature made of? A question that misunderstands the nature of what we're trying to explain. The fabric of space-time isn't just the stage for the cosmic drama, it's the leading actor, the script, and the theater itself, all woven together in a performance that becomes more mysterious the closer we look. Wow. In the summer of 1969, as Neil Armstrong was taking humanity's first steps on the moon, a team of physicists was preparing to test one of the strangest predictions ever made. That time itself runs slower in Earth's gravitational field. They took 4 extremely precise atomic clocks and flew them around the world on commercial airliners. When the clocks returned, they had aged differently than identical clocks that stayed on the ground, exactly as Einstein had predicted decades earlier. The flying clocks, slightly farther from Earth's center, and therefore in a weaker gravitational field, had experienced time at a fractionally faster rate. This wasn't just a curious effect. It was direct evidence of something profound about the relationship between matter and space-time. Gravity isn't a force pulling objects together, as Newton imagined. Instead, mass and energy tell space-time how to curve, and that curvature is what we experience as gravity. To understand this dance, imagine you're holding a conversation with someone across a crowded room. In flat space-time, your words would travel in straight lines. But if a massive object, say, a black hole, sits between you, space-time curves around it. Your words still travel along the straightest possible paths, but those paths are now curved through the geometry of warped space-time. From your perspective, it looks like your words are being deflected by a gravitational force, but really, they're just following the contours of curved reality. This relationship is perfectly reciprocal. Just as mass curves space-time, the curvature of space-time tells mass how to move. It's a cosmic choreography where neither partner leads. They respond to each other in an eternal dance governed by Einstein's field equations. The more massive an object, the more dramatically it warps space-time around it. Our sun, for instance, creates a gentle depression in the fabric of reality, like a marble resting on a stretched rubber sheet. Earth rolls around this depression in what we call an orbit. But from space-time's perspective, our planet is simply following the straightest possible path through curved geometry. But when matter becomes extremely dense, the dance becomes violent. Consider a neutron star, a city-sized sphere containing more mass than our sun. The space-time around such an object is so severely warped that time slows to a crawl. If you could somehow survive standing on its surface, you would experience time passing normally, but observers far away would see you moving as if trapped in slow motion. At the extreme end of this spectrum lie black holes, where the dance between matter and space-time reaches its climax. Here, matter has become so dense that it punches a hole in space-time itself, creating a region where the curvature becomes infinite, what physicists call a singularity. The boundary around this region, the event horizon, represents the point where space-time is so curved that even light cannot escape. But black holes aren't cosmic vacuum cleaners, indiscriminately sucking up everything around them. They're more like cosmic whirlpools, dragging space-time itself into rotation. As they spin, they twist the fabric of reality around them in a phenomenon called frame dragging. Near a rotating black hole, the very definitions of space and time become scrambled. Space flows like a river, and time becomes twisted into knots. This intimate relationship between matter and space-time creates some of the most beautiful phenomena in the universe. When two black holes spiral toward each other, they create ripples in space-time that propagate outward at the speed of light. These gravitational waves carry away energy, causing the black holes to spiral inward faster and faster until they collide in a cataclysmic merger that rings space-time like a cosmic bell. The energy released in these collisions is staggering. In the final fraction of a second, the merging black holes can radiate more power in gravitational waves than all the stars in the observable universe emit in light. Yet this energy isn't matter or radiation in any conventional sense. It's pure geometry, the curvature of space-time itself propagating across the cosmos. Recent observations have revealed that this dance between matter and space-time is even more intricate than Einstein imagined. Quantum effects near black holes suggest that information falling into them might be encoded on their surfaces, creating a holographic relationship between the volume of space and the information it contains. The dance continues, and with each new discovery, we realize that the partnership between matter and space-time is not just the foundation of gravity, it might be the key to understanding consciousness, information, and the very nature of existence itself. On September 14, 2015, at precisely 9:50 UTC, two machines separated by 3,000 kilometers detected something extraordinary, the fabric of space-time itself rippling like the surface of a pond. The signal lasted only 0.2 seconds. It was so subtle that it stretched and compressed the 4-kilometer arms of the LIGO detectors by less than 1/10,000th the width of a proton, a distance so small that if you scaled Earth up to the size of our solar system, this displacement would be smaller than the thickness of a human hair. Yet in that brief whisper, the universe revealed one of its most profound secrets. Space-time doesn't just exist, it speaks. The gravitational waves that LIGO detected had traveled for 1.3 billion years, carrying the acoustic signature of two black holes in their final death spiral. As these cosmic titans circled each other, accelerating to incredible speeds in their last moments, they stirred space-time into such violent motion that ripples spread outward in all directions, like a stone dropped into a cosmic pond. But here's what makes this discovery so revolutionary. For the first time in human history, we were reading information encoded in the very structure of reality itself. Light can be absorbed, scattered, or blocked by matter, but gravitational waves pass through everything, virtually unchanged. They carry pure information about spacetime's response to the most extreme events in the universe. The waves LIGO detected told a complete story. From the initial slow spiral, scientists could determine the masses of the two black holes, 36 and 29 times the mass of our Sun. As the frequency increased, revealing the accelerating orbital dance, they could track the objects getting closer and closer. Finally, in the last few milliseconds, the signal reached a crescendo and then suddenly stopped, marking the moment when two black holes became one. This wasn't just an observation. It was like listening to a cosmic symphony written in the language of curved spacetime. Each gravitational wave carries a unique signature, a fingerprint that reveals the nature of whatever created it. Binary neutron stars produce different patterns than black hole mergers. A collapsing stellar core creates a different signature than two black holes spiraling together. Since that first detection, we've learned to read an entirely new form of cosmic communication. We've detected dozens of black hole mergers, each one teaching us something new about how spacetime responds to extreme conditions. We've observed neutron star collisions that created gravitational waves while simultaneously producing gamma-ray bursts, optical flashes, and heavy elements like gold and platinum, giving us our first multi-messenger view of cosmic catastrophes. But gravitational waves have revealed something even more profound about the nature of spacetime itself. Unlike electromagnetic waves, which are disturbances in electric and magnetic fields that propagate through spacetime, gravitational waves are disturbances in spacetime itself. The gravitational waves are disturbances in spacetime itself. The gravitational waves have revealed something even more profound about the nature of spacetime itself. Unlike electromagnetic waves, which are disturbances in electric and magnetic fields that propagate through spacetime, the gravitational waves are disturbances in spacetime itself. When they pass through you right now, and they are constantly, from sources throughout the universe, your body, the Earth, and everything around you is being gently stretched and compressed in a rhythm that carries information from the farthest reaches of the cosmos. This means spacetime has a property that Einstein never fully anticipated: memory. When a gravitational wave passes through a region of space, it leaves behind a permanent displacement, a subtle change in geometry that persists long after the wave has moved on. Spacetime, in other words, remembers what has happened to it. Scientists are now building increasingly sensitive detectors to read these cosmic fingerprints. The European Virgo detector has joined LIGO in creating a global network that can pinpoint the source of gravitational waves in the sky. Japan's Kagra detector adds another ear to this cosmic conversation. And in space, the upcoming LISA mission will use laser interferometry between spacecraft separated by millions of kilometers to detect gravitational waves that are too long to be observed on Earth. These space-based detectors will open entirely new chapters in the story of spacetime. They'll be sensitive to waves produced by supermassive black holes at the centers of galaxies, binary star systems throughout the Milky Way, and possibly even the gravitational wave background left over from the first fraction of a second after the Big Bang, the cosmic equivalent of the microwave background radiation. Perhaps most tantalizing, these detectors might reveal gravitational waves from sources we haven't even imagined yet. Just as radio astronomy discovered pulsars, quasars, and the cosmic microwave background, phenomena that optical telescopes could never have detected, gravitational wave astronomy is opening a completely new sensory experience of the universe. The implications extend far beyond astronomy. By reading the fingerprints that cosmic events leave in spacetime, we're learning about the fundamental nature of reality itself. We're discovering that spacetime is not just the stage for the cosmic drama, but an active participant that carries information, has memory, and responds to events in ways that reveal the deep structure of existence. Every gravitational wave that washes over Earth is a message from the universe, written in the most fundamental language possible, the geometry of spacetime itself. We're finally learning to read these cosmic hieroglyphs, and what they're telling us is rewriting our understanding of everything from the birth of black holes to the nature of existence itself. The universe has been trying to tell us its secrets all along. We're finally learning to listen. Right now, as you read these words, you are participating in the universe's greatest magic trick, the creation of the arrow of time. Consider the coffee cooling in your mug, the dust settling on your bookshelf, the inevitable decay of the radioactive atoms in your smoke detector. In each case, energy is spreading out, becoming less concentrated, less useful, less organized. This isn't just a tendency, it's a fundamental law of nature, so basic that it defines the very direction of time itself. Yet here's the paradox that has puzzled physicists for over a century. If you filmed these processes and played the movie backward, every frame would show events that perfectly obey the laws of physics. There's nothing in the fundamental equations governing particles and forces that requires time to flow forward rather than backward. At the microscopic level, the universe appears to be completely time-symmetric. So where does time's arrow come from? The answer lies in one of the most profound concepts in all of science, entropy. But entropy isn't just about things becoming messier, as it's often described. It's about the fundamental relationship between information, probability, and the nature of existence itself. Imagine you walk into a room and find all the air molecules crowded into one corner, while the rest of the room is in perfect vacuum. You would immediately know you're watching a movie played backward, because such a configuration is so improbable that it essentially never occurs naturally. The molecules don't want to spread out. There are simply vastly more ways for them to be distributed throughout the room than concentrated in one corner. This is the deep insight that Ludwig Boltzmann provided in his statistical interpretation of the second law of thermodynamics. Entropy is a measure of the number of microscopic arrangements that correspond to a given macroscopic state. High entropy states are those with many possible microscopic configurations, while low entropy states have very few. But here's where the mystery deepens. If entropy always increases, as the second law demands, then the universe should have started in a state of extremely low entropy. And indeed, when we look back toward the Big Bang, we find exactly that, a universe that began in a state of almost inconceivable order and simplicity. Think about this carefully. The early universe was nearly perfectly uniform, with only tiny fluctuations in density and temperature. From our perspective, this seems like maximum disorder, just a smooth, featureless soup of particles and radiation. But from the perspective of gravity, this represents a state of incredibly low entropy. Gravity wants to clump matter together, create structure, form stars and galaxies and black holes. A smooth, uniform distribution of matter is, gravitationally speaking, as far from equilibrium as possible. This initial low entropy state is what cosmologists call the past hypothesis, the assumption that the universe began in a highly ordered configuration. Without this assumption, the second law of thermodynamics wouldn't work. Causality would break down, and the arrow of time would disappear. But why should the universe have started this way? This question has led physicists to some of the most speculative and profound ideas in modern cosmology. Perhaps our universe is just one bubble in an eternal, ever-expanding multiverse, where different regions have different initial conditions. In most regions, entropy starts high and stays high, so no arrow of time emerges. But in rare regions like ours, random fluctuations create pockets of low entropy that can evolve toward higher entropy states, generating the flow of time we experience. Or perhaps the arrow of time is connected to the expansion of space-time itself. As the universe expands, it creates new space, providing room for entropy to increase. The stretching of space-time might be what allows isolated systems to evolve from order to disorder, making the cosmic expansion and the thermodynamic arrow of time two aspects of the same fundamental process. Some physicists have proposed even more radical ideas. What if time's arrow emerges from consciousness itself? This might sound mystical, but there are serious theoretical reasons to consider it. The act of measurement in quantum mechanics seems to break time reversal symmetry, selecting specific outcomes from quantum superpositions. If consciousness involves quantum processes, then the arrow of time might be intimately connected to the emergence of observers who can remember the past but not the future. Recent research in quantum thermodynamics has revealed another layer of complexity. At the quantum level, the relationship between information and entropy becomes even more fundamental. When quantum information is destroyed, say when particles fall into a black hole, the universe loses the ability to reconstruct past states from present ones. This irreversible loss of information might be what prevents time from flowing backward, even in principle. But perhaps the most mind-bending possibility is that time's arrow is not fundamental at all, but rather an emergent property of our perspective within a timeless reality. In this view, called the block universe, all moments past, present, and future exist with equal reality. The flow of time we experience is like a spotlight illuminating different cross-sections of this four-dimensional block, creating the illusion of temporal passage. If this is correct, then asking why time flows forward is like asking why we experience space as three-dimensional rather than two-dimensional. It's not that space has an inherent widthness or heightness. These are just descriptions of our particular perspective within a higher dimensional reality. Similarly, the arrow of time might be a feature of consciousness rather than a fundamental property of the universe. This has profound implications for our understanding of causality, free will, and the nature of existence. If all moments exist equally, then in some sense, nothing ever truly ends. Your childhood, your present moment reading these words, and your future self, looking back on this memory, are all equally real, separated, not by the flow of time, but by their position in the four-dimensional geometry of space-time. Yet even if time's arrow is ultimately illusory, it remains the organizing principle of our existence. Without it, there would be no distinction between cause and effect, no possibility of memory or learning, no foundation for meaning or purpose. The arrow of time doesn't just tell us which way the universe is heading. It defines what it means to exist as conscious beings in a cosmos that somehow generated the capacity to understand itself. The universe began in a state of impossible order and is evolving toward maximum disorder. Yet along the way, it has created islands of ever-increasing complexity: stars, planets, life, consciousness, and intelligence. We are the universe's way of experiencing its own arrow of time, witnesses to the cosmic process that brought us into being and will eventually carry us beyond. In 1971, physicists Hathaway and Keating packed 4 atomic clocks onto commercial airliners and flew them around the world. When they landed, the clocks had aged differently than identical clocks left on the ground, some running faster, some slower, depending on their direction of flight and altitude. This wasn't science fiction. It was direct, measurable proof that time is not the universal constant we intuitively believe it to be. Time is negotiable, flexible, and relative, a dimension that can be stretched, compressed, and manipulated just like space. The key insight came from Einstein's recognition that there's no such thing as absolute motion. When you're sitting in a train moving at constant velocity, no experiment you can perform inside the train will tell you whether you're moving or stationary. Physics looks exactly the same in all inertial reference frames. But this symmetry comes with a price. Observers in relative motion will disagree about the timing and spacing of events. Consider 2 observers, Alice and Bob. Alice is on a train moving at high speed, while Bob stands on the platform. As Alice passes Bob, they both set their clocks to 0. From Bob's perspective, Alice's clock runs slower than his, a phenomenon called time dilation. But here's the crucial point. From Alice's perspective, it's Bob's clock that runs slower. Each observer sees the other's time as dilated. This isn't just a measurement error or an optical illusion. It's a fundamental feature of reality. Time dilation becomes more pronounced as velocities approach the speed of light. At 90%, the speed of light, time passes about 2.3 times slower for the moving observer. This isn't just a measurement error or an optical illusion. It's a fundamental one, the moving observer. Answer: at 99% the speed of light, it's about 7 times slower. At 99.9% the speed of light, it's over 22 times slower. For particles in cosmic ray showers, this effect is literally life-saving. Muons created high in Earth's atmosphere should decay long before reaching the ground. Their natural lifetime is only 2.2 microseconds, far too short for them to travel the 15 kilometers or so from the upper atmosphere to sea level, even at near light speed. Yet we detect them regularly at ground level because, from our perspective, their high-speed motion has slowed their internal clocks, allowing them to live much longer than they would if they were at rest. But velocity isn't the only thing that affects the flow of time. Gravity does too, and in an even more dramatic way. The stronger the gravitational field, the slower time passes, an effect called gravitational time dilation. This happens because gravity and acceleration are equivalent, as Einstein realized in his happiest thought. Someone in freefall can't tell whether they're falling in a gravitational field or floating in empty space. The Global Positioning System provides a daily demonstration of gravitational time dilation. GPS satellites orbit about 20,000 kilometers above Earth's surface, where gravity is weaker than at ground level. As a result, atomic clocks on the satellites run about 45 microseconds per day, faster than identical clocks on Earth. This might seem insignificant, but GPS requires nanosecond precision. Without constantly correcting for relativistic effects, GPS would accumulate errors of about 10 kilometers per day, making the system useless. Near more massive objects, the effects become even more extreme. On the surface of a neutron star, where gravity is 200 billion times stronger than Earth's, time passes about 30% slower than it does in empty space. If you could somehow survive standing on such an object for what felt like 1 hour, observers far from the neutron star would measure that about 1.4 hours had passed. At the event horizon of a black hole, gravitational time dilation becomes infinite. From the perspective of a distant observer, time slows to a complete stop. A clock falling into a black hole would appear to freeze at the event horizon, its hands never quite reaching the moment of crossing. Yet, from the clock's perspective, time passes normally. It crosses the event horizon and continues falling toward the singularity in a finite amount of proper time. This leads to one of the most mind-bending paradoxes in physics. If you fall into a black hole, you experience crossing the event horizon in a finite time, but external observers never see you cross. From their perspective, you remain frozen at the horizon forever, your image becoming increasingly redshifted and dim until it fades from view. Recent theoretical work suggests that time dilation might be even more fundamental than previously thought. Some physicists propose that the flow of time emerges from quantum entanglement between different regions of space. In this view, time dilation occurs because strong gravitational fields, or high velocities, affect the quantum entanglement that generates temporal flow. This opens up fascinating possibilities for the future. If we could manipulate quantum entanglement on macroscopic scales, we might be able to create artificial time dilation effects, allowing for practical time travel into the future. While traveling backward in time remains prohibited by causality, traveling forward at different rates might become technologically achievable. The implications extend beyond physics into philosophy and human experience. If time is relative, what does it mean to say that events happen now? If there's no universal present moment, how do we understand the nature of existence, consciousness, and free will? Time is not the rigid framework we once thought it was, but a flexible dimension woven into the fabric of space-time itself. Understanding its negotiable nature doesn't just change how we see the universe, it changes how we see ourselves as temporal beings existing within an infinitely stranger reality than our ancestors ever imagined. Close your eyes and try to catch the present moment. Feel it right now. This instant of consciousness, this singular now that separates your memories from your anticipations. Hold on to it. Gone. It's slipped away, replaced by another now and another in an endless stream of vanishing moments that create your experience of temporal flow. Yet, according to Einstein's equations, the moment you just try to grasp, along with every other moment in your life, exists with the same reality as this one. past, present, and future are equally real, equally there, spread out across the four-dimensional landscape of space-time like cities along a highway. This is perhaps the most unsettling consequence of relativity, the death of the universal now. In our pre-relativistic understanding, simultaneity was absolute. When something happened now on Earth, there was a corresponding now everywhere else in the universe, on Mars, in the Andromeda galaxy, in the most distant quasars. The present moment was like a cosmic knife edge, cutting through the universe and separating the fixed past from the uncertain future. Einstein's revelation destroyed this comfortable picture. If there's no absolute reference frame, there can be no universal now. Events that are simultaneous for one observer occur at different times for observers in relative motion. The present moment isn't a cosmic phenomenon. It's a local, subjective experience that varies from observer to observer. This leads to what physicists call the block universe, or eternalist view of time. Imagine space-time as a loaf of bread, with spatial dimensions represented by the width and height of each slice, and time represented by the length of the loaf. Each slice represents a three-dimensional snapshot of the universe at a particular moment. Now here's the crucial insight. The entire loaf exists simultaneously. Your birth is one slice. This moment is another slice, and your death is yet another slice. But they're all equally real. The only reason you experience temporal flow is that your consciousness traces a path through the loaf, experiencing each slice sequentially and creating the illusion of moving from past to future. But if this is true, what happens to free will? If your future already exists as definitively as your past, are your choices already determined? This question has troubled philosophers and physicists for over a century. Some argue that compatibilism, the idea that free will can coexist with determinism, resolves the paradox. Others suggest that quantum mechanics introduces genuine randomness that preserves meaningful choice. The block universe view also raises profound questions about the nature of consciousness itself. If all moments exist equally, why do we remember the past, but not the future? The answer might lie in the thermodynamic arrow of time. Our brains create memories by increasing entropy, a process that naturally points toward the future. Consciousness doesn't create the flow of time. Rather, the thermodynamic arrow creates consciousness's temporal orientation. Some physicists have proposed that time's flow is an emergent property of quantum mechanics. In this view, the process of quantum decoherence, the transition from quantum superposition to classical reality, creates a preferred direction in time. The future is quantum and indeterminate, while the past becomes classical and fixed through the accumulation of measurements and interactions. Recent work in quantum gravity suggests an even more radical possibility that time itself might be emergent, arising from more fundamental, timeless processes. Just as temperature emerges from the collective motion of atoms, time might emerge from the collective behavior of quantum information. In this view, asking when did an event happen might be like asking what's the temperature of a single atom, a question that misunderstands the nature of what we're trying to measure. The implications are staggering. If time is emergent, then at the most fundamental level, reality might be timeless. The equations of quantum gravity might describe a universe where nothing happens, nothing changes, nothing becomes, where all possibilities exist in an eternal, static superposition. Yet somehow, from this timeless foundation, the arrow of time emerges, consciousness arises, and we find ourselves as temporal beings, able to contemplate our own existence within the block universe. We are patterns in space-time that have become complex enough to experience their own unfolding, to remember their past configurations, and to anticipate their future ones. If we kan mat, view the view of the myth is third. Einstein himself found this view deeply troubling. When his lifelong friend Mikhail Besso died, Einstein wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Yet even he struggled to accept the full implications of his own theory. The eternal present of physics doesn't diminish the importance of our temporal experience. It transforms it into something even more remarkable than we imagined. Take a deep breath. In the air filling your lungs right now, there's a small but non-zero probability that all the oxygen molecules will spontaneously migrate to one corner of your room, leaving you gasping in a vacuum. The chance is so astronomically small, less than 1 in 10 circumflex 10 circumflex 25, that it would never happen even if you waited longer than the age of the universe. But according to quantum mechanics, it's possible. This is our first hint that at the deepest level, reality is far stranger than Einstein's already mind-bending relativity suggests. While relativity revealed that space and time are unified and flexible, quantum mechanics goes further. It suggests that at the smallest scales, space itself dissolves into a fizzing foam of probability and uncertainty. The quantum world operates by rules so foreign to our everyday experience that even physicists who work with them daily struggle to understand their implications. In the realm of the very small, particles don't have definite positions until they're observed. They exist in multiple states, simultaneously, and the very act of measurement doesn't just reveal reality, it helps create it. Consider the famous double-slit experiment, perhaps the most profound demonstration of quantum weirdness ever devised. Fire electrons one at a time through 2 parallel slits, and they create an interference pattern on a detector screen, just like waves would. Consider the famous double-slit experiment, perhaps the most profound demonstration. This suggests each electron somehow passes through both slits simultaneously, interfering with itself. But here's where it gets truly bizarre. If you place detectors at the slits to determine which path each electron takes, the interference pattern disappears. The electrons start behaving like classical particles, each taking a definite path through one slit or the other. The very act of observation changes the fundamental nature of the system. This isn't just true for electrons, it's true for everything. The chair you're sitting on, the device you're reading this on, your own body, everything is composed of quantum particles that exist in superpositions of multiple states until observation collapses them into classical reality. But quantum mechanics challenges our understanding of space in even more fundamental ways. At scales smaller than the Planck length, about 10 circumflex 35 meters, the smooth geometry of Einstein's spacetime breaks down completely. At these distances, quantum fluctuations become so violent that the very concept of a well-defined position becomes meaningless. Imagine zooming in on what appears to be a smooth surface, first with a magnifying glass, then with a microscope, then with increasingly powerful instruments. At first, the surface looks perfectly flat, but as your resolution increases, you begin to see tiny bumps and valleys. Zoom in further, and you discover that each bump is made of smaller bumps. Each valley contains smaller valleys. Keep going, and eventually you reach a scale where the surface no longer looks like a surface at all, but like a chaotic, roiling foam. This is what happens to spacetime at the Planck scale. The smooth four-dimensional manifold of general relativity gives way to what physicists call quantum foam, a seething mass of virtual particles constantly popping into and out of existence, creating a texture in space itself that defies our classical understanding of geometry. These virtual particles aren't just mathematical abstractions, they have measurable effects. Place 2 uncharged metal plates extremely close together in a perfect vacuum, and they'll be pushed together by the Casimir effect, a force created by virtual particles in the quantum vacuum. The empty space between the plates contains fewer virtual particles than the space outside, creating a pressure difference that pushes the plates together. This reveals something profound. What we call empty space is actually teeming with activity. The quantum vacuum is not empty at all, but filled with zero-point energy, the minimum energy that quantum fields must have, even in their ground state. Some calculations suggest this vacuum energy should be enormous, potentially infinite. That it doesn't rip space-time apart is one of the deepest mysteries in physics. The quantum nature of space also manifests in another deeply puzzling way: quantum tunneling. Particles can pass through barriers that should be impossible to cross according to classical physics. They don't go over or around these barriers. They literally tunnel through them, temporarily borrowing energy from the quantum vacuum to bridge regions of space that should be forbidden. This tunneling isn't rare or exotic. It's happening constantly throughout your body. The fusion reactions that power the sun rely on quantum tunneling to overcome the electrical repulsion between protons. The decay of radioactive atoms in your smoke detector happens through quantum tunneling. Even the synapses in your brain may depend on quantum tunneling effects for their operation. Perhaps most remarkably, some interpretations of quantum mechanics suggest that the act of observation doesn't just collapse probability waves, it might actually participate in creating the spatial relationships between objects. In this view, space isn't a pre-existing stage where quantum events unfold, but rather an emergent property that arises from the quantum interactions between particles. This dissolving of space into probability has profound implications for our understanding of reality. If space itself is quantum mechanical, then at the deepest level, the universe might not have a definite structure at all, but exist in a superposition of all possible geometries simultaneously. This dissolving of space into probability has profound implications for our understanding of reality. We're not just observers of quantum reality, we're participants in its creation, our measurements and interactions helping to weave the fabric of space itself from the quantum foam of possibility. You are, at this very moment, performing one of the most mysterious acts in all of physics. You are collapsing quantum superpositions simply by observing the world around you. The light hitting your eyes from this screen exists in a quantum superposition until the moment it strikes your retina. The electrons in your device's processor exist in multiple states simultaneously until they interact with other particles. Even the atoms in your body maintain quantum coherence until something, measurement, interaction, observation, forces them to choose a single, definite state. This is the measurement problem, one of the deepest puzzles in quantum mechanics. How and why does the fuzzy probabilistic quantum world give rise to the sharp, definite classical world we experience? According to the mathematical formalism of quantum mechanics, particles exist in superpositions of all possible states until they're measured. Schrödinger famously illustrated this with his thought experiment about a cat that's simultaneously alive and dead until someone opens the box to look. The mathematics is crystal clear. Unmeasured quantum systems evolve according to the Schrödinger equation, maintaining perfect superpositions indefinitely. But something dramatic happens during measurement. The superposition instantly collapses. The quantum system suddenly chooses one outcome from all the possibilities, and we observe a definite result. This collapse appears to be instantaneous, non-local, and fundamentally different from any other process in physics. The mystery deepens when we ask what constitutes a measurement. Does it require a conscious observer? Does a sophisticated detector qualify? What about a simple interaction between particles? Where exactly do we draw the line between the quantum realm of superpositions and the classical world of definite states? Some physicists, following the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, argue that measurement is simply a fundamental feature of quantum mechanics that doesn't require deeper explanation. The quantum formalism works perfectly for predicting experimental results, they argue, so we shouldn't worry about the philosophical implications of wave function collapse. But others find this deeply unsatisfying. Hugh Everett III proposed a radical alternative, the many worlds interpretation. In this view, wave functions never actually collapse. Instead, every possible outcome of every quantum measurement actually occurs, but in separate, parallel branches of reality. When you measure a quantum system, you don't collapse its superposition. You simply find yourself in one particular branch of an ever-branching multiverse. This resolves the measurement problem by eliminating it entirely. There is no collapse, no special role for consciousness, no boundary between quantum and classical realms. Every possible history plays out in some branch of the multiverse. The cat is both alive and dead, just in different worlds. Yet another approach suggests that consciousness itself plays a crucial role in wave function collapse. Some interpretations propose that the complex information processing that occurs in conscious brains is somehow responsible for transforming quantum possibilities into classical actualities. In this view, observation by a conscious mind is what breaks the quantum superposition and creates definite reality. Recent experimental work has added new dimensions to the measurement problem. Quantum error correction experiments have shown that information about quantum states can be preserved even while individual particles interact with their environment. This suggests that the boundary between quantum and classical behavior is more complex and controllable than previously thought. The decoherence program offers yet another perspective. Instead of mysterious wave function collapse, decoherence theory suggests that quantum superpositions appear to collapse when systems become entangled with their environment. The superposition doesn't actually disappear. It just becomes so spread out across the environment that it's no longer observable in the original system. But decoherence raises its own questions. Why do some types of interaction cause decoherence, while others preserve quantum coherence? And why do we observe definite outcomes rather than experiencing the smeared-out superpositions that decoherence theory predicts? Perhaps most intriguingly, some physicists are exploring the possibility that space-time itself emerges from quantum measurements. In this view, the act of measurement doesn't just determine the properties of particles, it actually creates the spatial and temporal relationships between events. Space and time, rather than being the stage where quantum dramas unfold, might be emergent properties that arise from the pattern of quantum measurements and interactions. The measurement problem isn't just a technical issue for quantum physicists. It strikes at the heart of our understanding of reality, consciousness, and existence itself. Every moment of your conscious experience involves the mysterious transition from quantum possibility to classical actuality. You are not just observing reality, you might be participating in its creation, one measurement at a time. In a laboratory in Vienna, a physicist measures the spin of an electron and finds it spinning clockwise. At that exact instant, in a laboratory in Tokyo, another electron, one that has never been in contact with the first, suddenly knows to spin counterclockwise. No signal passes between them, no force connects them. Yet somehow, the measurement in Vienna instantaneously determines the state of the particle in Tokyo. This is quantum entanglement, and it represents perhaps the most profound challenge to our understanding of space, time, and the nature of reality itself. Einstein called it spookhaft Fernwirkung, spooky action at a distance, and spent decades trying to prove it impossible. He failed. Nature, it turns out, is far spookier than even Einstein could accept. To understand why entanglement is so revolutionary, we need to grasp what physicists call locality, the principle that objects are only directly influenced by their immediate surroundings. If you want to affect something far away, you need to send some kind of signal or influence through the intervening space. This seems so obvious that it's built into the foundation of both relativity and our everyday understanding of causality. But quantum entanglement violates locality in the most fundamental way possible. When two particles become entangled, say, by being created together in a single quantum process, they form a unified quantum system that transcends spatial separation. Measure one particle, and you instantly know something about the other, regardless of how far apart they are. The weirdness goes deeper than mere correlation. Before measurement, neither particle has a definite state. They exist in a quantum superposition of all possibilities. The entangled system as a whole has definite properties, but these properties are not distributed among the individual particles. Instead, the particles share a single quantum state that spans the entire distance between them. This isn't just theoretical speculation. John Bell proved in 1964 that entanglement makes predictions that no local realistic theory can match. Bell's inequalities provide a mathematical test to distinguish between a universe where particles have definite properties independent of measurement, local realism, and a universe where quantum entanglement is real. Decades of experiments have consistently violated Bell's inequalities, confirming that entanglement is indeed a feature of our reality. The most recent experiments have closed all the major loopholes, that might have allowed local explanations, leaving us with an inescapable conclusion. The universe is fundamentally non-local. But entanglement challenges more than just locality. It challenges our understanding of space itself. If entangled particles share a single quantum state regardless of spatial separation, what does it mean to say they are far apart? The quantum connection between them appears to exist outside of space, in some sense transcending the geometric relationships that define our ordinary experience. Some physicists have proposed that entanglement might be more fundamental than space itself. In this view, space emerges from the pattern of quantum entanglements between particles. The geometry of spacetime, rather than being the arena where quantum processes unfold, might be a consequence of the network of quantum correlations that connect all the particles in the universe. This idea gains support from research in quantum gravity, where physicists are discovering deep connections between entanglement and the structure of spacetime. The holographic principle, for instance, suggests that the information contained in a volume of space can be encoded on its boundary, a relationship that depends crucially on quantum entanglement between different regions. Recent work has shown that entanglement can even create emergent spacetime geometry. In certain theoretical models, two regions of space that are far apart according to ordinary geometry can be connected by quantum entanglement in a way that creates a wormhole, a shortcut through spacetime that effectively makes the regions neighbors in the quantum sense. This leads to a startling possibility. What we experience as the separation between objects in space might be an illusion created by our classical perspective. At the quantum level, everything might be intimately connected through a web of entanglement that transcends spatial distance. The implications extend beyond physics into information theory and philosophy. Entanglement allows for quantum information processing that's impossible with classical systems. Quantum computers exploit entanglement to perform certain calculations, exponentially faster than classical computers. Quantum cryptography uses entanglement to create communication channels that are fundamentally secure against eavesdropping. But entanglement also raises profound questions about the nature of identity and individuality. If particles can share quantum states across vast distances, are they really separate entities? When entangled particles maintain their connection, regardless of spatial separation, it suggests that individuality itself might be an emergent property rather than a fundamental feature of reality. Some interpretations of quantum mechanics take this even further. In the many worlds interpretation, entanglement doesn't create mysterious connections between distant particles. Instead, it creates correlations between different branches of the universal wave function. When you measure one particle of an entangled pair, you don't affect the distant particle. Rather, you find yourself in a branch of reality where the correlations are exactly what quantum mechanics predicts. Perhaps most remarkably, recent experiments have demonstrated entanglement not just between particles, but between larger and larger systems. Scientists have entangled molecules, then small crystals, then microscopic mechanical oscillators. There appears to be no fundamental limit to the size of systems that can exhibit quantum entanglement. This raises the tantalizing possibility that macroscopic objects, perhaps even living systems, might maintain quantum entanglement under certain conditions. Some researchers have speculated that quantum entanglement in biological systems might play a role in photosynthesis, bird navigation, and possibly even consciousness itself. The death of locality doesn't just change how we think about quantum mechanics. It transforms our understanding of what it means for things to be separate, distinct, or independent. In a universe where entanglement is fundamental, the classical notion of isolated objects interacting across empty space gives way to a more holistic view, where everything is connected through an invisible web of quantum correlations. We are not separate from the universe around us, observing it from the outside. We are entangled with it, our quantum states intertwined with every particle we've ever interacted with, connected to the cosmic web of relationships that might be more fundamental than space and time themselves. Einstein hoped to restore locality and realism to physics, but entanglement has shown us something far more profound. Reality is stranger, more interconnected, and more unified than we ever dared imagine. Imagine you could grab the universe like a cosmic movie reel and play it backward. Galaxies would rush toward each other. Stars would collapse into the gas clouds that formed them. Atoms would break apart into their constituent particles. Keep rewinding, and eventually you'd reach a moment about 13.8 billion years ago, when the entire observable universe was compressed into a region smaller than the period at the end of this sentence. This is our current best understanding of cosmic history. The universe began in an event we call the Big Bang, when space, time, matter, and energy all came into existence simultaneously. But here's what makes this story so extraordinary. We're not just telling a tale about the distant past. We're following a trail of evidence that leads us backward through time, to what might be the very beginning of time itself. The evidence is written across the sky in multiple forms. First, there's the expansion of space itself. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther they are, the faster they're receding. This isn't because they're moving through space. Space itself is expanding, carrying the galaxies with it like raisins in a rising loaf of bread. If space is expanding now, then it must have been smaller in the past. Run the clock backward far enough, and you reach a point where all the matter and energy in the observable universe was compressed into an infinitesimally small, infinitely dense point, what physicists call a singularity. But the expansion of space is just the beginning of the evidence.
In 1965, two Bell Labs scientists accidentally discovered the cosmic microwave background, a faint radio signal coming from every direction in the sky. This radiation is the afterglow of the Big Bang itself, the stretched-out remnant of the intense heat and light that filled the early universe. The cosmic microwave background is like a cosmic forensic report, encoding details about the universe when it was only 380,000 years old, the moment when the cosmos cooled enough for the first atoms to form. So, Uldomorni, Sitten Pa, Sitten Tuthen. Before this, the universe was so hot and dense that electrons couldn't stay bound to atomic nuclei. Free electrons scattered light constantly, making the universe opaque, like a thick fog. When atoms finally formed, the fog lifted, and light could travel freely for the first time. That ancient light has been traveling through space ever since, stretched by cosmic expansion from visible light into microwaves. When we observe the cosmic microwave background, we're literally seeing the universe as it was nearly 14 billion years ago. The precision of this cosmic photograph is stunning. Tiny temperature variations in the background radiation, differences of only a few millionths of a degree, reveal the quantum fluctuations that would eventually grow into galaxies, stars, and planets. We can see the seeds of cosmic structure frozen in time, preserved in the afterglow of creation itself. Another piece of evidence comes from the relative abundances of light elements in the universe, the Big Bang nucleosynthesis. The process by which the first atomic nuclei formed makes precise predictions about how much hydrogen, helium, and lithium should exist. Observations match these predictions with remarkable accuracy, providing an independent confirmation that the universe was once hot and dense enough for nuclear reactions to occur throughout space. But as we rewind the cosmic clock further back, our understanding becomes increasingly speculative. The first 3 minutes after the Big Bang are reasonably well understood through extrapolation from particle physics experiments. We can trace cosmic evolution back to when the universe was a hot soup of quarks and gluons, then further back to when it was dominated by pure energy in the form of photons and exotic particles. Yet the closer we get to the moment of the Big Bang itself, the more mysterious it becomes. At the Planck time, about 10 circumflex 43 seconds after the beginning, our current theories break down completely. This is the era when quantum effects dominated gravity, when the distinction between space and time might have lost all meaning, when the very concepts we use to understand physics ceased to apply. What happened during this Planck epoch remains one of the greatest mysteries in science. Our equations produce infinities and impossibilities. The singularity at the beginning of time represents not just extreme physical conditions, but a fundamental limit to what we can know using current physics. Some physicists argue
that asking what came before the Big Bang is meaningless, like asking what's north of the North Pole. If time itself began with the Big Bang, then there was no before in any meaningful sense. The universe didn't come into existence at a particular moment in time. Rather, time came into existence, along with everything else. Others suggest that the apparent singularity is an artifact of our incomplete understanding, and that a complete theory of quantum gravity will resolve the infinities and reveal what actually happened at the beginning. Perhaps the Big Bang was preceded by a big crunch, the collapse of a previous universe. Perhaps our cosmos is just one bubble in an eternal, ever-inflating multiverse. As we push backward toward time's beginning, we approach the ultimate frontier of human knowledge. We're not just exploring the history of the universe, we're investigating the nature of existence itself, seeking to understand how something can come from nothing, how time can have a beginning, and what it means for reality to have an origin. What came before the Big Bang? It's perhaps the most profound question humans have ever asked, and for decades, physicists dismissed it as meaningless. After all, if time itself began with the Big Bang, then asking what came before is like asking what's north of the North Pole, a category error that reveals a misunderstanding of the question itself. But in recent decades, theoretical physicists have developed sophisticated models suggesting that our Big Bang might not have been the beginning of everything, but rather a transition from a previous state of existence. These theories paint a picture of reality far grander and stranger than a simple creation ex nihilo. The most developed of these ideas is cosmic inflation, proposed by Alan Guth in 1980 and refined by many others since. Inflation theory suggests that in the first fraction of a second after the Big Bang, space expanded exponentially fast, far faster than the speed of light. In less than 10 circumflex 2 seconds, a region smaller than a proton inflated to the size of a grapefruit, smoothing out irregularities and setting the stage for the universe we observe today. But inflation theory leads to a startling conclusion. If inflation happened once, it probably happened everywhere and everywhen. The same quantum field that drove inflation in our region of space would be driving it in countless other regions as well, creating an endless cascade of bubble universes, each with its own Big Bang, its own physical laws, its own evolutionary history. This is the multiverse, not just multiple universes, but an infinite number of them, constantly being created as inflation continues in regions we can never observe. Our entire observable universe, with its 100 billion galaxies spread across 93 billion light-years, would be just one tiny bubble in an infinite cosmic foam of universes. Even more mind-bending is the possibility of eternal inflation. In this scenario, inflation never truly ends. It just gets interrupted in local regions by the formation of bubble universes like ours. While we experience the aftermath of our Big Bang, inflation continues in the space between bubbles, constantly creating new universes with different properties, different dimensions, even different forms of physics. Some of these universes might have physical constants very different from ours. In some, the force of gravity might be stronger or weaker. In others, there might be more or fewer spatial dimensions. Some universes might expand so rapidly that matter never has a chance to clump together into stars and galaxies. Others might collapse back on themselves before stars can form. This raises the profound question of why our universe has the particular properties it does. Why is gravity just strong enough to allow galaxy formation, but not so strong that the universe collapses immediately? Why do the fundamental forces have the precise strengths necessary for stellar nucleosynthesis and the chemistry of life? The multiverse provides a potential answer. Maybe our universe doesn't have special properties at all. Maybe every possible combination of physical laws and constants is realized somewhere in the infinite multiverse. We find ourselves in a universe compatible with our existence, not because it was designed that way, but because we could only emerge in such a universe. This is the anthropic principle. The idea that the apparent fine-tuning of our universe's parameters is explained by observer selection bias. But the multiverse hypothesis raises as many questions as it answers. If there are infinite universes with different physical laws, how do we make sense of probability? If everything that can happen does happen somewhere, what meaning can we assign to the particular sequence of events that led to our existence? Some physicists have proposed cyclical models of the universe, where our Big Bang was preceded by a big crunch, the collapse of a previous universe. In these models, the universe undergoes eternal cycles of expansion and contraction, with each cycle potentially having different properties. The Phoenix universe rises from the ashes of its predecessor, carrying forward some information while erasing other details. Even more speculative is the idea that our universe might be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. If the holographic principle is correct, then the Big Bang might represent not the creation of space and time, but the emergence of our three-dimensional experience from more fundamental, timeless information processing. Quantum mechanics adds another layer of mystery to the question of cosmic origins. Some interpretations suggest that the universe began as a quantum fluctuation in a pre-existing quantum vacuum. In this view, the Big Bang was the universe's way of choosing one particular configuration from an infinite sea of quantum possibilities. But what is a quantum vacuum, and how can it exist before space and time? These questions push us to the very limits of physical reasoning. Perhaps the pre-Big Bang state was not characterized by the presence of something, but by the absence of the classical concepts we use to understand reality. No space, no time, no matter, no energy, just pure potentiality waiting to actualize itself. Loop quantum cosmology, an approach that attempts to merge quantum mechanics with general relativity, suggests yet another possibility. In this theory, the Big Bang wasn't a beginning, but a big bounce, a transition from a contracting previous universe to our expanding one. The singularity is replaced by a quantum bridge, connecting two phases of cosmic evolution. Recent work in string theory has proposed that our universe might be a three-dimensional membrane floating in a higher dimensional space, called the bulk. Collisions between branes could trigger Big Bang events, making our cosmic origin the result of accidents in a higher dimensional reality we can never directly observe. Perhaps most radically, some physicists suggest that asking what came before the Big Bang assumes that causality and temporal sequence apply at the most fundamental level of reality. But if space and time themselves are emergent properties that arise from more basic quantum information processing, then the question of temporal precedence might be as meaningless as asking about the color of the number 7. These ideas remain highly speculative, pushing the boundaries of what science can meaningfully address. Yet they represent humanity's deepest attempt to understand the ultimate nature of existence, to answer not just how the universe began, but why there is something rather than nothing at all. We stand at the threshold of the knowable, peering into mysteries that may forever remain beyond the reach of empirical investigation, yet continue to inspire our greatest theoretical insights into the nature of reality itself. There exists a moment in cosmic history that represents the ultimate frontier of human knowledge, a barrier so fundamental that it may forever remain impenetrable to scientific investigation. This is the Planck epoch, the first 10 circumflex 43 seconds after the Big Bang, when our universe was so young, so hot, and so dense that the very concepts of space and time lose their meaning. To understand why this moment represents such an absolute limit, we need to grasp what happens when the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, converge at the energies that existed in the first instant of cosmic history. At the Planck temperature of about 10 circumflex, 32 Kelvin, often energy becomes so intense that quantum effects dominate gravity itself. At the Planck length of about 10 circumflex 35 meters, quantum uncertainty makes the very notion of a well-defined position meaningless. At the Planck time of 10 circumflex 43 seconds, causality itself breaks down as quantum fluctuations happen faster than information can propagate. These aren't just extremely small or large numbers. They represent fundamental limits imposed by the structure of reality itself. The Planck scale is where quantum mechanics and general relativity meet, and where our current theories simply stop working. The equations that successfully describe everything from the quantum behavior of atoms to the dynamics of black holes, produce infinities and nonsensical results when applied to the Planck epoch. This breakdown isn't a failure of human ingenuity or a temporary gap in our knowledge. It's a reflection of something deeper. The theoretical frameworks we use to understand the universe may be fundamentally insufficient to describe the conditions at the very beginning of time. Consider what this means for our cosmic origin story. We can trace the universe's evolution with remarkable precision from about 1 second after the Big Bang to the present day. We understand Big Bang nucleosynthesis, the formation of the first atoms, the emergence of stars and galaxies. We can even make educated guesses about what happened in the first fractions of a second when the universe was a hot soup of quarks and gluons. But the Planck epoch remains a black box. During those first 10 circumflex 43 seconds, the universe may have experienced its most crucial transformations. The emergence of space-time itself, the selection of physical laws and constants, the initial conditions that would determine everything that followed. Yet this epoch may remain forever beyond our ability to investigate directly. Some physicists argue that this represents a fundamental horizon of knowability, a boundary beyond which science cannot venture, not due to technological limitations, but because of the logical structure of reality itself. If space-time itself emerged during the Planck epoch, then concepts like cause and effect, before and after, and here and there, may not apply to the processes that gave birth to our universe. This doesn't mean we must abandon all hope of understanding cosmic origins. String theory, loop quantum gravity, and other approaches to quantum gravity offer glimpses of what might have happened during the Planck epoch. These theories suggest that the apparent singularity at t equals sine 0 might be resolved, replaced by more complex but finite processes that bridge the gap between nothing and something. But even if these theories prove correct, they may only push the horizon of unknowability back one step. If our universe emerged from a multiverse, what gave birth to the multiverse? If it arose from quantum fluctuations in a pre-existing vacuum, what determined the properties of that vacuum? Each answer seems to generate deeper questions, suggesting that the ultimate origin of existence might remain forever mysterious. This horizon of knowability has profound implications for human understanding. It suggests that there may be questions that science, for all its power and success, cannot answer, not because we lack the tools or intelligence, but because the questions themselves may transcend the logical categories that make scientific investigation possible. Yet, this limitation doesn't diminish the value of our cosmic quest. By pushing against the boundaries of the knowable, we expand our understanding of what it means to exist in a universe that somehow bootstrapped itself into being. We discover that the very fact that we can ask these questions, like that the universe has evolved conscious beings capable of contemplating their own origins, might be the most remarkable mystery of all. The Planck epoch remains a moment of infinite mystery, a cosmic event horizon beyond which our knowledge may never venture. But perhaps that's as it should be, a permanent reminder that reality is stranger and more wonderful than we can ever fully comprehend. Right now, as you read these words, you might be surrounded by entire dimensions of space that remain completely invisible to your senses. According to some of the most sophisticated theories in modern physics, the 3 spatial dimensions you experience, length, width, and height, may be just a tiny subset of a far richer, more complex geometric reality. This isn't science fiction speculation. It's a serious consequence of string theory, one of our most promising attempts to unify all the forces of nature into a single, elegant framework. But string theory comes with a startling requirement. For the mathematics to work, our universe must have more than the 4 dimensions of space-time we experience. Depending on the specific version of the theory, reality might contain 10, 11, or even 26 dimensions in total. Where are these extra dimensions? Why can't we see them? The answer lies in a concept that's as beautiful as it is mind-bending: dimensional compactification. Imagine you're looking at a garden hose from across a large field. From that distance, the hose appears to be a one-dimensional line. It has length, but no width or thickness. But if you walk closer, you discover that the hose actually has additional dimensions curled up so tightly that they were invisible from far away.
What seemed one-dimensional from a distance is actually three-dimensional up close. String theorists propose that something similar might be happening with space itself. The three dimensions we experience extend infinitely in all directions, but there might be additional dimensions curled up so tightly, perhaps at the Planck scale of 10 circumflex 35 meters, that we can't detect them directly. These compactified dimensions could exist at every point in our familiar three-dimensional space, creating a hidden architecture of reality that influences everything we experience. But why would extra dimensions be necessary at all? The answer lies in the fundamental problem that string theory was designed to solve: the incompatibility between quantum mechanics and general relativity. When physicists try to merge these two pillars of modern physics, they encounter infinities and contradictions that seem impossible to resolve. String theory offers an elegant solution by proposing that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings. Just as different vibrational modes of a guitar string produce different musical notes, different vibrational patterns of these fundamental strings would appear to us as different particles, electrons, quarks, photons, and so on. But here's the crucial point. These strings can only vibrate consistently in spaces with specific numbers of dimensions. The mathematics of string theory simply doesn't work in our familiar four-dimensional spacetime. It requires the additional dimensions to provide enough room for all the possible vibrational patterns that correspond to the particles and forces we observe. This leads to a remarkable possibility: the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might all be different aspects of string vibrations propagating through the full higher dimensional geometry of reality. What we experience as distinct forces might be unified aspects of a single higher dimensional phenomenon. The specific way that extra dimensions are compactified could determine the properties of our observable universe. Different shapes and sizes of the curled-up dimensions would produce different particle masses, different force strengths, even different numbers of particle families. The entire structure of physics, as we know it, might be determined by the hidden geometry of spaces we can never directly perceive. Some versions of string theory suggest that our entire three-dimensional reality might be confined to a brain, a membrane embedded in a higher dimensional space called the bulk. In this scenario, ordinary matter and most forms of energy are trapped on our brain, unable to access the additional dimensions. Only gravity, because it's a curvature of space-time itself, can propagate through the full higher dimensional space. This could explain why gravity is so much weaker than the other fundamental forces. The gravitational field lines might be spreading out through all the extra dimensions, diluting gravity's strength in our three-dimensional slice of reality. If we could somehow access the extra dimensions, gravity might be just as strong as the other forces. Recent experiments have tested this possibility by looking for deviations from Newton's inverse square law of gravitation at very short distances. If extra dimensions exist and are large enough, gravity should become stronger than expected at distances comparable to the size of the compactified dimensions. So far, these experiments have found no such deviations, but they continue to probe smaller and smaller scales. The implications of extra dimensions extend far beyond particle physics. They might provide a natural explanation for dark matter, the mysterious substance that makes up about 27% of the universe, but interacts only weakly with ordinary matter. Perhaps dark matter consists of particles that can access some of the extra dimensions, making them effectively invisible to our three-dimensional perspective. Extra dimensions might also offer new possibilities for space travel and communication. If we could learn to manipulate objects through higher dimensional space, we might be able to travel between distant points in our three-dimensional world by taking shortcuts through the hidden dimensions, a real-world version of the wormholes that appear in science fiction. But perhaps the most profound implication is philosophical. If extra dimensions exist, then our entire experience of reality is just a shadow, a projection of a far richer and more complex truth. We might be like prisoners in Plato's cave, mistaking the shadows on the wall for reality itself.
never suspecting the higher dimensional world that casts those shadows. Hold your hand up to a wall and shine a light on it. The shadow you see is a two-dimensional projection of your three-dimensional hand, a flattened representation that captures some information about the original object, but loses crucial details. Now imagine that you are the shadow, and somewhere in a higher dimensional space, your true self exists in its full geometric glory. This isn't just a metaphor. According to some interpretations of modern physics, our entire three-dimensional reality might be exactly this kind of shadow, a projection from a higher dimensional realm that contains the true, complete description of everything we experience. The idea that our world might be a shadow of higher dimensions has ancient roots. Plato's allegory of the cave described prisoners chained to face a wall, mistaking the shadows cast by objects behind them for reality itself. Only when freed from their chains could they turn around and see the three-dimensional objects that cast the shadows. Modern physics has given this ancient insight a precise mathematical framework. In general relativity, we've learned that three-dimensional space and one-dimensional time are unified into four-dimensional space-time. But what if even this four-dimensional space-time is itself just a shadow of something larger? Consider how shadows work in familiar space. When light from a three-dimensional object hits a two-dimensional surface, the shadow preserves some information, the outline, certain proportions, the general shape, while losing others, particularly depth. Remarkably, if you know the rules governing how shadows are cast, you can sometimes reconstruct information about the three-dimensional object by studying its two-dimensional projection carefully. String theory suggests that something analogous might be happening with our reality. Our familiar four-dimensional space-time might be a shadow cast by processes occurring in 10 or 11 dimensions. The particles we observe, the forces we experience, even the constants of nature that determine how our universe behaves, all of these might be projections from a higher dimensional source. This perspective offers elegant explanations for several mysteries in physics. Why do fundamental particles come in the specific families and arrangements we observe? Perhaps because these arrangements are the only patterns that can cast stable shadows into four-dimensional spacetime. Why do the fundamental forces have the particular strengths they do? Perhaps because these strengths are determined by the geometry of the higher dimensional space that projects into our reality. The shadow analogy also illuminates why extra dimensions might be invisible to us. Just as a shadow contains no direct information about the dimension perpendicular to the surface it's cast on, our four-dimensional experience might contain no direct access to the perpendicular dimensions of higher dimensional space. We can infer their existence from the patterns and properties of our projected reality, but we cannot step outside our dimensional prison to observe them directly. But unlike Plato's prisoners, we might not be helpless. Advanced experiments at particle accelerators, like the Large Hadron Collider, are searching for indirect evidence of extra dimensions. When particles collide at high energies, some of the collision products might escape into extra dimensions, appearing to us as missing energy that violates conservation laws in our three-dimensional accounting. Other experiments look for tiny deviations from the inverse square law of gravity at short distances. If gravity can propagate through extra dimensions while other forces cannot, then at distances comparable to the size of the compactified dimensions, gravity should become stronger than our three-dimensional equations predict. Some physicists have proposed that dark matter might consist of particles that exist partly in extra dimensions, making them invisible to electromagnetic interactions, while still affecting the gravitational curvature of space-time. From this perspective, dark matter isn't truly dark. It's simply casting its shadow into our dimensional slice from a higher dimensional space where it's perfectly visible. The holographic principle takes the shadow analogy to its logical extreme, suggesting that all the information in any volume of space can be encoded on its boundary. If this is correct, then the three-dimensional interior of any region might be entirely determined by two-dimensional information on its surface, making our experience of three-dimensional depth itself a kind of elaborate illusion. Perhaps most remarkably, some theories suggest that consciousness itself might be capable of accessing information from higher dimensions.
If our brains are quantum information processing systems, they might be able to tap into patterns and correlations that exist in the full higher dimensional space, giving us indirect access to realms beyond our ordinary perception. We may be shadows in higher dimensions, but we're shadows that have learned to think, to question, and to search for the higher dimensional reality that casts us into being. Everything you think you know about the three-dimensional world around you, the depth of the room you're in, the solidity of the objects you touch, even the volume of space your body occupies, might be an illusion. According to one of the most revolutionary ideas in modern physics, all the information that defines your three-dimensional reality could be encoded on a two-dimensional surface, like a cosmic hologram projecting the appearance of depth where none truly exists. This is the holographic principle, and it's not just science fiction speculation. It's a serious theoretical framework that has emerged from some of the deepest insights in black hole physics, quantum mechanics, and string theory. If it's correct, it would fundamentally transform our understanding of space, information, and reality itself. The principle originated from a puzzling discovery about black holes made by Stephen Hawking in the 1970s. Hawking showed that black holes emit radiation and gradually evaporate, eventually disappearing completely. But this created a profound paradox. If a black hole forms from matter that falls into it and then evaporates completely, what happens to the information that the original matter contained? In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but never eliminated entirely. Yet Hawking's calculations suggested that when a black hole evaporates, the information that fell into it would be lost forever, violating one of the most fundamental principles of quantum theory. The resolution to this paradox came from a startling insight. Perhaps the information that falls into a black hole is never actually stored in the three-dimensional interior we imagine. Instead, it might be encoded on the black hole's two-dimensional event horizon, its surface boundary. When the black hole evaporates, the information isn't lost, it's released back into the universe as part of the Hawking radiation. But Jacob Bekenstein and Stephen Hawking had already discovered something remarkable about black hole horizons: their entropy. The amount of information they can store is proportional not to their volume, as you might expect, but to their surface area. This suggests that the interior of a black hole doesn't actually contain more information than what can be encoded on its boundary. Gerard Hooft and Leonard Susskind took this insight to its logical conclusion. If the maximum information content of any region of space is determined by the area of its boundary rather than its volume, then perhaps three-dimensional space itself is an illusion. Maybe all the information we think exists throughout a volume of space is actually encoded on the surface that bounds that volume. This leads to a mind-bending conclusion. The room you're sitting in, with all its apparent three-dimensional depth, might be equivalent to information encoded on its walls, floor, and ceiling. You, your furniture, the air you breathe. Everything might be a projection from this two-dimensional encoding, like a hologram that creates the appearance of three-dimensional reality from two-dimensional information. The holographic principle gained powerful support from the AD-SECFT correspondence, discovered by Juan Maldacena in 1997. This mathematical framework shows that certain theories of quantum gravity in higher dimensional curved spacetime are exactly equivalent to quantum field theories on the boundary of that spacetime. In other words, physics in the three-dimensional interior can be completely described by different physics on the two-dimensional boundary. This isn't just a mathematical curiosity. It provides a concrete example of how holographic duality works. All the complexity we think exists in the bulk of space, including gravity itself, emerges from more fundamental processes occurring on the boundary. The interior dimension is literally projected from the boundary information. Recent experiments have begun to test holographic ideas directly. Physicists have created laboratory analogues of holographic systems using ultra-cold atoms and condensed matter systems. These experiments show that holographic duality isn't just a theoretical abstraction. It describes real physical relationships that can be observed and measured. The implications extend far beyond black holes and esoteric physics. If the holographic principle is fundamental,
It could revolutionize our understanding of consciousness, computation, and the nature of experience itself. Perhaps the rich, three-dimensional world of our conscious experience is a holographic projection from information processing occurring on the two-dimensional boundary of our neural networks. This might explain some puzzling features of consciousness, such as the binding problem, how our brains integrate information from many different sources into unified perceptions. If consciousness works holographically, then the integration might occur naturally as part of the projection process, with boundary information automatically creating unified interior experiences. The holographic principle also offers new insights into the nature of space and time. If three-dimensional space is emergent from two-dimensional boundary information, then space itself might not be fundamental, but rather a derived quantity that emerges from more basic information theoretic processes. This could help resolve the conflict between quantum mechanics and general relativity by showing that space-time geometry is not the arena where physics occurs, but rather a shadow cast by more fundamental quantum information dynamics. Some researchers have proposed that the entire universe might be holographic, with all the information in our three-dimensional cosmos encoded on a distant two-dimensional boundary. This cosmic holography could explain why the universe appears flat and uniform on large scales. These might be natural consequences of projecting from a smooth boundary. But holography raises profound questions about the nature of reality and our place within it. If we're holographic projections, what does that make us? Are we real in any meaningful sense, or are we just patterns of information encoded on a distant boundary? Do our experiences have the depth and richness we believe, or are they elaborate illusions created by the projection process? Perhaps these questions miss the point. Even if we're holographic, our experiences are still genuine features of reality. They're just encoded and projected in ways that differ radically from our intuitive understanding. The love you feel, the beauty you perceive, the thoughts you think, these remain real experiences, whether they're generated by three-dimensional neural activity or two-dimensional information processing. The holographic principle doesn't diminish reality. It reveals that reality is far more subtle, elegant, and interconnected than we ever imagined. We might be living in a cosmic hologram, but if so, it's a hologram capable of experiencing wonder at its own existence, of questioning its own nature, and of discovering the deep mathematical principles that govern its projection into being. The apparent depth of our world might be an illusion, but it's an illusion that has somehow learned to contemplate the boundary from which it's projected. What if the universe is not made of matter and energy, but of information and computation? What if every particle interaction, every quantum measurement, every moment of cosmic evolution is actually a computational process, reality executing itself like the most sophisticated program ever conceived? This isn't the stuff of science fiction. It's a serious hypothesis, gaining ground among physicists, computer scientists, and philosophers who are discovering deep connections between the fundamental laws of physics and the principles of information processing. They're finding that, at its most basic level, reality might be computational in nature. Consider what happens during any physical process. When two particles collide, information about their properties, mass, charge, spin, momentum, gets processed according to the laws of physics to determine the outcome. The rules of quantum mechanics specify how probabilities are calculated, how wave functions evolve, how measurements collapse superpositions into definite states. In other words, the universe appears to be constantly performing calculations. But it goes deeper than metaphor. John Wheeler, one of the great physicists of the 20th century, proposed that reality is fundamentally informational with his famous phrase, "it from bit." In Wheeler's vision, every physical quantity derives from binary choices, from bits of information. The basic question is not what is the universe made of, but what questions is the universe answering? Quantum mechanics provides compelling evidence for this view. The quantum state of any system can be completely described by information, specifically by the probabilities associated with all possible measurement outcomes. When we interact with a quantum system, we're not uncovering pre-existing properties. We're participating in the computational process by which reality determines what properties to manifest. The computational perspective offers elegant explanations for several mysterious features of our universe. Why does nature seem to respect conservation laws, the conservation of energy, momentum, electric charge, and other quantities? Perhaps because these laws represent computational constraints, requirements for any information processing system to remain consistent and stable over time. Why does the universe have a maximum speed, the speed of light? In a computational system, information can only propagate at a finite rate. The speed of light might be the universe's maximum data transfer rate, the fundamental limit on how quickly information can be processed and communicated between different parts of the cosmic computer. Even more intriguingly, the discrete nature of quantum mechanics, the fact that energy, angular momentum, and other quantities come in indivisible packets called quanta, resembles the digital nature of computation. Just as computers process information in discrete bits, the universe might process reality in discrete quantum units. Some physicists have proposed that space and time themselves emerge from underlying computational processes. In this view, the smooth, continuous space-time of general relativity is like the continuous motion we see on a computer screen. It appears smooth, but is actually composed of discrete computational steps occurring at the Planck scale. Ed Fredkin, one of the pioneers of digital physics, proposed that the universe is literally a cellular automaton, a discrete computational system, where simple rules applied to local information generate complex, emergent behavior. In Fredkin's vision, what we call physical laws are just the programming rules of the cosmic computer. This computational view gains support from the holographic principle, which suggests that all the information in any volume of space can be encoded on its boundary. If space is fundamentally informational, then the holographic bound makes perfect sense. It's simply a limit on how much information can be stored and processed in any region. Recent work in quantum information theory has revealed deep connections between entanglement, computation, and the structure of spacetime. Some researchers propose that space itself is woven from quantum entanglement, that geometric relationships between objects are really informational relationships between the bits that describe them. The computational hypothesis even offers new insights into consciousness. If the universe is fundamentally computational, then consciousness might be a natural property of sufficiently complex information processing systems. The human brain, with its roughly 86 billion neurons and trillions of connections, might be a biological computer that has achieved sufficient computational sophistication to become self-aware. But this raises profound questions about the nature of existence and identity. If you're a pattern of information processing rather than a collection of matter, what happens to your sense of self? Are you the program, the data, or the computation itself? If the pattern that constitutes you could be copied or transferred to another substrate, would that copy be you or someone else? The digital universe hypothesis also suggests startling possibilities for the future. If reality is computational, then in principle, it might be possible to hack reality, to discover and exploit the fundamental algorithms that govern cosmic evolution. Advanced civilizations might be able to reprogram aspects of space, time, and matter by accessing the universe's underlying code. Even more speculatively, if our universe is a computation, what is the computer running it? Some philosophers and physicists have seriously proposed that we might be living in a simulation, that our entire reality is being computed by some vastly superior civilization or process. While this remains highly speculative, it highlights how the computational view of reality challenges our most basic assumptions about existence. Whether or not the universe is literally computational, the information theoretic perspective is transforming our understanding of physics. It's revealing that information and computation are not just tools we use to understand reality. They might be the most fundamental aspects of reality itself. We are not just observers of cosmic computation. We are part of it, patterns of information that have become complex enough to contemplate the computational process that brought us into being. Imagine zooming into a photograph on your computer screen. At first, the image appears smooth and continuous, But as you magnify it further and further, you eventually begin to see the individual pixels, discrete, indivisible units of information that combine to create the appearance of continuous imagery. Now, imagine doing the same thing with space itself. According to some of the most radical proposals in modern physics, space might not be the smooth, infinitely divisible continuum that our everyday experience suggests. Instead, at the smallest possible scales, distances around the Planck length of 10 circumflex 35 meters, space might be pixelated, composed of discrete, indivisible units that combine to create the illusion of continuity, just like the pixels on your screen. This isn't just idle speculation. The idea that space might be fundamentally discrete or emerges from serious attempts to reconcile quantum mechanics with general relativity. When physicists try to apply quantum principles to gravity and space-time, they encounter fundamental problems that suggest our concept of smooth, continuous space breaks down at the smallest scales. The Planck length represents a natural candidate for the size of these space pixels. This distance is derived from fundamental constants, the speed of light, Planck's constant, and Newton's gravitational constant, and it represents the scale at which quantum effects become as important as gravitational effects. At distances smaller than the Planck length, quantum uncertainty becomes so severe that the very concept of a well-defined distance loses meaning. If space is pixelated at the Planck scale, then the universe would be like a cosmic display screen with a resolution of about 10 circumflex 35 pixels per meter. This is far, far finer than any human technology. To put it in perspective, if a proton were enlarged to the size of Earth, the space pixels would still be smaller than atoms. Loop quantum gravity, one of the leading approaches to quantum gravity, provides a concrete framework for understanding discretized space. In this theory, space is not made of points, but of tiny loops and networks that weave together at the Planck scale. The smooth geometry of general relativity emerges from the collective behavior of these discrete elements, much like how the fluid properties of water emerge from the motion of individual molecules. The pixelated structure of space would have profound implications for our understanding of the universe. For one thing, it would place fundamental limits on how much information can be stored in any region of space. Each space pixel could encode only a finite amount of information, creating a cosmic version of the bandwidth limitations that constrain digital systems. This discretization might also explain some puzzling features of quantum mechanics. The uncertainty principle, which prevents us from knowing both the position and momentum of a particle with perfect precision, might be a natural consequence of space's pixelated structure. If space comes in discrete units, then position itself becomes fundamentally uncertain at the smallest scales. The pixel hypothesis also offers new perspectives on black holes and the information paradox. If space is discrete, then black holes would have a finite, countable number of internal states, exactly what's needed to give them well-defined entropy. The Hawking radiation that causes black holes to evaporate might be the universe's way of reading out the information stored in these discrete states. Some physicists have proposed that the expansion of the universe might be driven by the creation of new space pixels. As the cosmos evolves, it might be generating new pixels of space, causing the overall volume to increase. This could provide a natural explanation for dark energy, the mysterious force causing cosmic expansion to accelerate. The discrete structure of space might even be detectable. Some theories predict that light traveling vast distances through pixelated space would show tiny deviations from perfect straight-line propagation. Observations of gamma rays from distant galaxies are searching for these subtle effects, trying to measure whether space itself has a granular structure. If space is indeed pixelated, it would represent one of the most fundamental discoveries in the history of science, revealing that continuity itself is an illusion that emerges from underlying discreteness. Everything we experience as smooth motion through continuous space would actually be discrete jumps from pixel to pixel, happening so rapidly and at such small scales that we perceive seamless flow. This would make the universe quite literally digital at its foundation, a cosmic computer processing reality, one Planck-scale pixel at a time. generating the rich, continuous world of our experience from the discrete substrate of quantized spacetime. We would be living not just in a digital simulation, but in a reality that is fundamentally digital in its very structure. What if time doesn't flow like a river, but ticks like a clock? What if each moment isn't a point on a continuous timeline, but rather a discrete computational step in the universe's algorithmic execution of reality? This radical reconceptualization of time emerges from the intersection of physics, computer science, and information theory. If the universe is fundamentally computational, a vast information processing system, then time might be the sequence of computational steps that transforms one state of reality to the next. Think about how time works in a computer simulation. The program doesn't experience smooth, continuous time. Instead, it executes in discrete steps. The processor performs one calculation, updates the state of the system, then moves to the next calculation. The appearance of smooth motion and continuous change is an illusion created by performing these updates rapidly enough that they blur together. In this view, what we call the flow of time might be the universe updating itself from one computational state to the next. Each tick of cosmic time would correspond to a fundamental computational operation, a quantum measurement, a particle interaction, an information processing event that advances the universal algorithm by one step. The Planck time, approximately 10 circumflex 40, 3 seconds, provides a natural candidate for the duration of these computational steps. This is the smallest interval of time that has any physical meaning, derived from the same fundamental constants that give us the Planck length. Just as space might be pixelated at the Planck scale, time might be quantized into discrete Planck duration moments. If time is algorithmic, it would explain why the laws of physics are mathematical. Mathematical equations wouldn't just describe how the universe behaves. They would literally be the code that the universe executes. The Schrödinger equation, Maxwell's equations, Einstein's field equations, these might be the subroutines of cosmic computation, the algorithms that determine how each quantum of time transforms the universal state. This perspective offers new insights into the arrow of time, why time flows forward rather than backward. In any algorithmic process, there's a natural direction from input to output, from initial conditions to computed results. The arrow of time might simply be the direction of cosmic computation, the sequence in which the universal algorithm processes information. The second law of thermodynamics, which states that entropy always increases, might be a computational principle rather than a purely physical one. Entropy is fundamentally a measure of information, specifically a measure of how much information is needed to describe a system's microscopic state. The increase of entropy might represent the accumulation of computational complexity as the universal algorithm generates increasingly sophisticated patterns of information. But if time is computational, what is the universe computing? One possibility is that it's solving its own existence, continuously calculating what should happen next based on current conditions and the laws of physics. Each moment would be the result of the universe asking itself, given the current state of all matter and energy, what should the next state be? Another possibility is that the universe is computing all possible quantum outcomes simultaneously. In the many worlds interpretation of quantum mechanics, every quantum measurement splits reality into multiple branches, each corresponding to a different possible outcome. If this is correct, then cosmic computation might be generating an enormous branching tree of parallel realities, with our experience timeline being just one branch of this vast quantum calculation. The algorithmic view of time also provides new perspectives on consciousness and free will. If time is a sequence of computational steps, then consciousness might be a complex subroutine within the universal algorithm, a pattern of information processing that has become sophisticated enough to model itself and its environment. This raises profound questions about the nature of choice and determinism. If you're part of a universal computation, are your decisions predetermined by the algorithm, or do they represent genuine input that influences how the computation unfolds? Some theories suggest that consciousness might introduce true randomness into the cosmic algorithm, making the future genuinely open rather than determined. Recent work in quantum computing has revealed deep connections between time, computation, and information. Quantum computers can perform certain calculations exponentially faster than classical computers, quantum superposition, and entanglement. If the universe is fundamentally quantum computational, it might be processing reality using quantum algorithms that are far more powerful than anything classical physics suggests. The algorithmic time hypothesis also offers tantalizing possibilities for time travel and temporal manipulation. If time is computational, then in principle, it might be possible to access previous states of the universal algorithm, like loading an earlier save file in a computer game. While this remains highly speculative, it suggests that the nature of time might be more flexible than our everyday experience suggests. Perhaps most remarkably, if time is algorithmic, then the future might already exist, in a sense not as a predetermined outcome, but as the set of all possible computational branches that the universal algorithm could follow. Each moment would be the universe selecting one path from the vast space of algorithmic possibilities. This transforms time from a mysterious flow that carries us from past to future into something more concrete and understandable. The step-by-step execution of the cosmic program that generates reality. We are not passive observers being carried along by time's current. We are active participants in the algorithm, patterns of computation that have become complex enough to influence the very process that creates us. Every moment is a computational miracle, a quantum of time in which the universe calculates itself into the next moment of existence. Right now, you are experiencing one of the deepest mysteries in all of existence, the flowing subjective sense of time that carries you from moment to moment. You feel the present as it slips into the past, anticipate the future as it approaches, and somehow bind all these temporal experiences into the unified stream of consciousness that defines your existence as a thinking being. Yet, according to the equations of physics, this flowing time you're experiencing doesn't exist. Einstein's relativity revealed that there is no universal now, no cosmic present moment that defines simultaneity across the universe. The block universe interpretation of space-time suggests that all moments, past, present, and future, exist with equal reality, spread out across the four-dimensional landscape of space-time, like scenes in a cosmic movie reel. Quantum mechanics complicates the picture further, suggesting that the future might be fundamentally uncertain, while the past becomes fixed through the accumulation of measurements and interactions. Yet even in quantum mechanics, the mathematical formalism is largely timeless. The Schrödinger equation describes how probability waves evolve, but it doesn't explain why we experience this evolution as a flowing present moment. This is what philosopher David Chalmers calls the hard problem of consciousness, but applied specifically to our experience of time. The hard problem asks, why is there subjective first-person experience at all? Why don't we simply process information like sophisticated computers without any inner sense of what it's like to be us? The temporal version of this question is equally profound. Why do we experience time as flowing when physics suggests it doesn't flow at all? Consider what makes your experience of time unique. When you remember yesterday, you don't just access stored information, you experience a qualitative sense of pastness, a feeling that those events are behind you in time. When you anticipate tomorrow, you don't just process predictions, you experience futurity, a sense that those events are approaching through time. And right now, you experience presentness, a feeling of being at the leading edge of time as it unfolds. These qualitative aspects of temporal experience, what philosophers call temporal qualia, seem to have no place in the mathematical description of physics. You can describe a clock measuring intervals, but you can't capture in equations the felt experience of duration. You can describe the correlation between brain states and memories, but you can't explain why remembering feels different from anticipating. Some neuroscientists argue that the flow of time is a construction of the brain, created by the way our neural networks process and integrate information. Our brains are constantly building models of reality. and the sense of temporal flow might be how these models represent the relationship between different states of information processing. The brain doesn't experience the present moment directly. It takes time for sensory information to be processed, integrated, and made available to consciousness. What we call now is actually a constructed present, typically lasting about 2-3 seconds, during which the brain binds together information from different senses and different processing pathways into a unified conscious experience. But this neural explanation, while fascinating, doesn't solve the hard problem of temporal consciousness. It explains the mechanisms by which brains process temporal information, but it doesn't explain why those mechanisms are accompanied by subjective experience at all. Why isn't there just information processing without the inner sense of temporal flow? Some physicists and philosophers have proposed that consciousness might be fundamentally temporal in nature, that the experience of flowing time is not something consciousness has, but something consciousness is. In this view, consciousness is the universe's way of experiencing its own temporal evolution, the subjective aspect of whatever process transforms one moment into the next. This connects to ideas about consciousness and quantum mechanics. Some interpretations suggest that consciousness plays a special role in collapsing quantum superpositions, transforming quantum possibilities into classical actualities. If this is correct, then conscious observers might be actively participating in the creation of definite reality, moment by moment. Roger Penrose and Stuart Hameroff have proposed that consciousness arises from quantum processes in microtubules within neurons. In their theory, consciousness corresponds to moments when quantum superpositions collapse in the brain, creating discrete, unified conscious experiences. Roger Penrose and Stuart Hameroff have proposed that consciousness arises from quantum processes in microtubules within neurons. Each moment of consciousness would correspond to a quantum measurement event, giving consciousness a fundamental temporal granularity. Other researchers have explored the possibility that consciousness is inherently quantum mechanical, existing in superpositions of different states, until observation or interaction causes it to collapse into definite experiences. This could explain why consciousness seems to have a temporal flow. It might be constantly collapsing from quantum uncertainty into classical certainty, creating the experience progression from possibility to actuality. But perhaps the most profound possibility is that subjective time is not an illusion to be explained away, but a fundamental feature of reality that physics hasn't yet learned to incorporate. What if the flowing present moment is real, and the timeless equations of physics are just approximations that work well for practical calculations, but miss something essential about the nature of existence? Some physicists have proposed that time's flow emerges from the quantum information processing that occurs throughout the universe. In this view, the second law of thermodynamics doesn't just describe the increase of entropy, it describes the creation of time itself, as quantum information becomes irreversibly processed into classical information. The relationship between consciousness and time might be even more intimate than we realize. If consciousness is fundamentally about integrating information across time, binding past memories, present perceptions, and future expectations into unified experiences, then perhaps consciousness and temporality are two aspects of the same phenomenon. This could explain why disorders of consciousness often involve disruptions of temporal experience. Patients with certain types of brain damage lose the ability to form new memories, trapping them in an eternal present. Others experience temporal fragmentation, unable to bind experiences across time into coherent narratives. These clinical observations suggest that consciousness and temporality are deeply intertwined at the neural level. The hard problem of subjective time remains one of the deepest challenges at the intersection of physics, neuroscience, and philosophy. We can measure time with extraordinary precision, trace its role in the fundamental laws of physics, and map its neural correlates in the brain. But the mystery of why time feels the way it does, why there is something it's like to exist as a temporal being, remains as profound as ever. Perhaps this mystery is not a problem to be solved, but a feature of reality to be embraced. The flowing stream of consciousness through time, what might be the universe's greatest achievement, the evolution of matter and energy into patterns, complex enough to experience their own temporal existence, to wonder about their place in the cosmic story, and to seek understanding of the very mystery they embody. Every time you look at the world around you, you are performing an act of cosmic creativity. According to some interpretations of quantum mechanics, your observation doesn't just reveal reality, it participates in creating it, selecting specific outcomes from an infinite sea of quantum possibilities. This isn't mystical speculation. It's a consequence of one of the most well-established and puzzling features of quantum mechanics, the measurement problem. When quantum systems are isolated from their environment, they exist in superpositions of multiple states simultaneously. But the moment they're observed or measured, the superposition instantaneously collapses into a single, definite outcome. Consider the famous double-slit experiment, which revealed the wave-particle duality of matter. When electrons are fired one at a time through two parallel slits, they create an interference pattern on a detector screen, clear evidence that each electron somehow passes through both slits simultaneously, like a wave. But place detectors at the slits to determine which path each electron takes, and the interference pattern disappears. The electrons start behaving like classical particles, each taking a definite path through one slit or the other. The mere act of observation fundamentally changes the nature of reality at the quantum level. This isn't because the measurement apparatus physically disturbs the system. The effect occurs even with the most gentle, non-invasive measurements. It's as if reality exists in a state of quantum indeterminacy until conscious observation forces it to choose specific properties. But what constitutes an observation? This question has puzzled physicists for nearly a century. Does it require a conscious mind, or is any interaction with a measuring device sufficient? Does the detector itself observe the particles, or must a human look at the detector's readout? Where exactly do we draw the line between the quantum realm of superpositions and the classical world of definite properties? Some interpretations of quantum mechanics give consciousness a central role in the collapse of the wave function. In this view, consciousness is not just an emergent property of complex matter arrangements, it's a fundamental feature of reality that participates in the selection of which quantum possibilities become actual. The physicist Eugene Wigner illustrated this with a thought experiment involving his friend in a laboratory. Wigner's friend performs a quantum measurement and observes a definite result. But from Wigner's perspective outside the lab, the entire system, including his friend, remains in a quantum superposition until Wigner himself observes the outcome. This suggests that consciousness might have a hierarchical structure, with higher levels of observation collapsing the superpositions of lower levels. Recent experiments have tested aspects of Wigner's thought experiment, showing that different observers can indeed disagree about the outcomes of quantum measurements until they communicate and compare their results. This has led to the startling conclusion that facts might not be universal, but instead depend on the perspective of the observer. The role of consciousness in quantum mechanics extends beyond individual measurements to the structure of reality itself. If conscious observation helps determine which quantum outcomes become real, then the existence of conscious observers throughout cosmic history might have played a role in shaping the universe we inhabit. This connects to the anthropic principle, the observation that the universe appears to be fine-tuned for the existence of conscious observers. Perhaps this fine-tuning isn't a cosmic coincidence or evidence of design, but rather a consequence of the participatory role that consciousness plays in selecting which version of reality becomes actualized. Some physicists have proposed that consciousness might be the universe's method of exploring its own potential states. In this view, every conscious observation represents the universe asking itself a question about its nature, with the measurement outcome being the answer. The evolution of consciousness throughout cosmic history would then represent an ever-increasing capacity for the universe to explore and determine its own properties. The many worlds interpretation offers a different perspective on the observer's role. In this view, all possible quantum outcomes actually occur, but in separate, parallel branches of reality. Conscious observers don't collapse wave functions, they simply find themselves in one particular branch of an ever-branching multiverse. Each measurement creates new branches, with different versions of the observer experiencing different outcomes. But even in the many worlds interpretation, Consciousness plays a crucial role in defining what we mean by branches and outcomes. The structure of reality depends on how conscious observers pass their experiences into distinct possibilities and definite results. Recent work in quantum information theory has revealed deep connections between observation, information, and the structure of space-time itself. The act of measurement doesn't just determine the properties of particles, it might actually create the spatial and temporal relationships between events. In this view, space-time itself emerges from the pattern of quantum observations and measurements. If consciousness plays a fundamental role in creating reality, then we are not passive witnesses to the cosmic drama, but active participants in its unfolding. Every moment of conscious experience represents a collaboration between mind and universe, a process by which potential becomes actual, possibility becomes reality. This transforms our understanding of human existence from something incidental to cosmic evolution into something central to the universe's self-actualization. We are not just complex arrangements of matter that happen to be conscious. We are consciousness incarnate, the universe's way of experiencing and determining its own nature. The observer effect suggests that the ancient philosophical question, if a tree falls in a forest and no one hears it, does it make a sound, might have a deeper answer than we ever imagined. Without observers to collapse quantum superpositions, the tree might not even have a definite position, much less make a definite sound. Look around you. Notice the delicate balance that makes your existence possible. Gravity strong enough to hold planets together, but weak enough to allow stars to burn for billions of years. Electromagnetic forces precisely calibrated to allow complex chemistry while keeping atoms stable. A universe old enough for heavy elements to form in stellar cores, but young enough that stars still shine. You exist in a cosmos that appears to be exquisitely fine-tuned for the emergence of conscious observers like yourself. Change any of the fundamental constants of nature by even tiny amounts, and the universe would be a barren wasteland where consciousness could never arise. Behave in tiny amounts. So, this observation forms the foundation of the anthropic principle, one of the most controversial and profound ideas in modern cosmology. At its core, the principle suggests that the universe's properties are constrained by the requirement that it be capable of producing observers who can contemplate those properties. Consider the evidence for this fine-tuning. If the strong nuclear force were just 2% weaker, atomic nuclei couldn't hold together, and there would be only hydrogen in the universe. If it were 2% stronger, hydrogen would be so rare that stars couldn't form. If the electromagnetic force was slightly different, carbon and oxygen couldn't both be stable, making carbon-based chemistry impossible. The expansion rate of the universe appears equally fine-tuned. If the early universe had expanded slightly faster, matter would never have clumped together to form stars and galaxies. If it had expanded slightly slower, the universe would have collapsed back on itself long before complex structures could emerge. Even more remarkably, the universe seems fine-tuned for the production of the heavy elements necessary for life. The processes that forge carbon, oxygen, and other essential elements in stellar cores require incredibly precise nuclear resonances. Fred Hoyle famously predicted the existence of a specific energy level in carbon-12 nuclei solely because life exists, and later experiments confirmed his prediction. These observations raise a profound question. Why is the universe so perfectly suited for consciousness? There are several possible answers, each with radical implications for our understanding of reality and our place within it. The first possibility is design, that the universe was intentionally created with conscious observers in mind. While this explanation satisfies some philosophical and religious perspectives, it doesn't address the deeper question of why any universe should exist at all, designed or otherwise. A second possibility is the multiverse hypothesis. If there are countless universes with different physical constants and laws, then it's not surprising that we find ourselves in one of the rare universes that allows consciousness to emerge. We couldn't observe a universe that doesn't permit observers to exist. This is the weak anthropic principle. Our existence explains why we observe life-friendly conditions, not because the universe was designed for us, but because we could only emerge in a universe compatible with our existence. The strong anthropic principle goes further, suggesting that the universe must have properties that allow consciousness to develop at some point in its history. This implies that consciousness is not just an accidental byproduct of cosmic evolution, but a necessary feature that constrains the possible nature of reality itself. Some physicists have proposed that consciousness might play an active role in determining the properties of the universe through quantum mechanical processes. If conscious observation helps collapse quantum superpositions, then the presence of observers throughout cosmic history might have participated in selecting which version of physical reality becomes actualized. This leads to the most radical interpretation, the participatory anthropic principle, which suggests that consciousness and cosmos are co-creative, each one helping to bring the other into existence. In this view, the universe evolves toward complexity and consciousness, while consciousness participates in determining which cosmic possibilities become real. Recent discoveries in cosmology have added new dimensions to anthropic reasoning. The existence of dark energy, which causes cosmic expansion to accelerate, appears to be another fine-tuned feature. If dark energy were much stronger, galaxies and stars could never form. If it were much weaker, the universe might have recollapsed before complex structures could develop. But the anthropic principle also raises troubling questions about the nature of scientific explanation. If we explain the universe's properties by pointing to the requirement that observers exist, are we engaging in legitimate science or circular reasoning? How can we test hypotheses that depend fundamentally on our own existence? Perhaps the anthropic principle's greatest insight is not about cosmic fine-tuning, but about the deep connection between mind and cosmos. Whether through design, selection, or participation, consciousness appears to be intimately woven into the fundamental structure of reality. We are not accidental observers of an indifferent universe, but essential participants in a cosmic story that somehow requires our presence to be complete. We stand at the threshold of a revolution in our understanding of space and time. After a century of wrestling with the incompatibilities between quantum mechanics and general relativity, physicists are developing radical new theories that promise to transform our conception of reality itself. The problem is clear. General relativity describes gravity as the curvature of smooth, continuous spacetime, while quantum mechanics suggests that at the smallest scales, everything, including space and time, should be subject to quantum uncertainty and discreteness. When physicists try to merge these two pillars of modern physics, they encounter infinities, paradoxes, and breakdowns that signal the need for a completely new framework. The leading candidate for this new framework is string theory, which proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny vibrating strings. These strings exist in 10 or 11 dimensions, with the extra dimensions compactified at scales so small we can't detect them directly. Different vibrational patterns of these strings would appear to us as different particles: electrons, quarks, photons, and even gravitons, the hypothetical particles that carry gravitational force. String theory is mathematically elegant and potentially capable of unifying all the fundamental forces, but it remains frustratingly difficult to test experimentally. The energy scales at which string effects become apparent are far beyond what any conceivable particle accelerator could reach. Critics argue that string theory has become more mathematics than physics, generating thousands of possible solutions, but few testable predictions. If you see testable predictions, an alternative approach is loop quantum gravity, which attempts to quantize space-time itself. In this theory, space is not smooth and continuous, but composed of discrete loops and networks at the Planck scale. These quantum loops weave together to create the appearance of smooth spacetime at larger scales, much like the threads in a fabric create the appearance of a continuous surface. Loop quantum gravity makes specific predictions about the nature of black holes and the early universe. It suggests that the Big Bang was preceded by a big bounce, the collapse and rebound of a previous universe. Black holes, rather than containing infinitely dense singularities, would have quantum cores that eventually explode, releasing their contents back into the universe. Even more radical is emergent gravity, championed by physicists like Eric Verlinde. This approach suggests that gravity is not a fundamental force at all, but an emergent phenomenon arising from the statistical behavior of quantum information. Just as temperature emerges from the collective motion of atoms, gravity might emerge from the way information is distributed throughout spacetime. If emergent gravity is correct, then spacetime itself might be an emergent phenomenon, arising from more fundamental quantum information processes. This would represent a complete inversion of our traditional understanding. Instead of matter existing in spacetime, spacetime would exist in matter, or more precisely, in the information that constitutes matter. The holographic principle, discussed earlier, is evolving into increasingly sophisticated theories about the nature of reality. The ADES-CFT correspondence has revealed that certain theories of quantum gravity in higher dimensions are mathematically equivalent to quantum field theories on the boundary of those dimensions. This suggests that the interior of space might be entirely encoded in information on its surface. Recent work has extended holographic ideas beyond theoretical physics into practical applications. Physicists are using holographic methods to understand strongly correlated quantum systems, superconductors, and even aspects of nuclear physics. The holographic principle is transforming from an exotic speculation into a practical tool for understanding complex quantum systems. Perhaps the most promising development is the growing recognition that quantum entanglement might be fundamental to the structure of spacetime itself. The ER=EPR conjecture, proposed by Maldacena and Susskind, suggests that quantum entanglement and spacetime wormholes are two descriptions of the same phenomenon. If this is correct, then the geometry of space might emerge from the pattern of quantum entanglements between particles. This has led to the development of quantum error correction approaches to spacetime, which suggest that the stability and structure of space and time might be maintained by quantum error correction mechanisms, similar to those used in quantum computers to protect information from decoherence. The implications of these emerging theories extend far beyond academic physics. If spacetime is emergent from quantum information, then in principle, it might be possible to manipulate space and time by controlling quantum information. This could lead to technologies that seem like science fiction today: artificial gravity, faster-than-light communication through extra dimensions, or even limited forms of time travel. But perhaps the most profound implication is philosophical. These theories suggest that reality at its most fundamental level is not material, but informational. The universe might be, in Wheeler's phrase, it from bit, everything that exists arising from quantum information processing. As we develop quantum computers and explore the boundaries between information, computation, and physics, we might discover that the distinction between virtual and real, between simulation and reality, is not as clear as we once believed. We might find that consciousness, computation, and cosmos are all aspects of a single underlying informational reality. The next few decades promise to be the most exciting in the history of physics, as these emerging theories mature into testable predictions and new technologies. We are on the verge of understanding space and time, not as the fixed stage for physical events, but as dynamic, emergent, and potentially malleable aspects of a deeper quantum reality. The future of our understanding of space and time will be written not just in theoretical equations, but in the laboratories, observatories, and quantum computers that are pushing the boundaries of what we can observe, measure, and manipulate. Consider the technological revolution that has already transformed our understanding of spacetime. The IGO and Virgo gravitational wave detectors have given us the ability to hear spacetime itself vibrating, detecting distortions smaller than 1/10,000th the width of a proton. These instruments have opened an entirely new window onto the universe, allowing us to observe black hole mergers, neutron-star collisions, and potentially even the gravitational wave background left over from the first moments after the Big Bang. The next generation of gravitational wave detectors will be even more sensitive. The European Space Agency's LISA mission will place 3 spacecraft in a triangular formation millions of kilometers apart, using laser interferometry to detect gravitational waves in space. Halls. This space-based detector will be sensitive to much longer wavelength gravitational waves
potentially revealing the gravitational signatures of supermassive black holes, binary star systems throughout the galaxy, and cosmic events we haven't even imagined yet. But perhaps the most revolutionary technological development is the emergence of quantum technologies that allow us to manipulate the fundamental quantum properties of matter and space-time. Quantum computers, which use quantum superposition and entanglement to process information in ways impossible for classical computers, are beginning to simulate quantum systems that are too complex for classical analysis. These quantum simulations are providing new insights into the relationship between quantum mechanics and space-time. Researchers are using quantum computers to explore theories of quantum gravity, simulate black hole interiors, and test ideas about emergent space-time. As quantum computers become more powerful, they may allow us to probe aspects of quantum gravity that are impossible to explore through theoretical calculation alone. Atomic clocks have become so precise that they can detect gravitational time dilation over distances of just a few centimeters. Future atomic clock networks could map the gravitational field of Earth with unprecedented precision, potentially revealing the structure of space-time in ways that could test predictions of quantum gravity theories. The Large Hadron Collider and its planned successors are probing higher and higher energy scales, searching for evidence of extra dimensions, quantum black holes, and other exotic phenomena predicted by theories of quantum gravity. While we may never reach the Planck scale energies, where quantum gravity effects become dominant, we might find indirect evidence of higher dimensional physics in the debris of high-energy particle collisions. Advances in neuroscience and brain imaging are providing new insights into the nature of consciousness and its relationship to time. As we develop better understanding of how the brain processes temporal information and generates the subjective experience of flowing time, we may discover whether consciousness plays a fundamental role in the collapse of quantum superpositions or the structure of space-time itself. Perhaps most intriguingly, we are beginning to explore the boundaries between physical and digital reality. Virtual and augmented reality technologies are creating increasingly convincing simulations of space and time, while advances in artificial intelligence are creating systems that can model and manipulate complex physical processes. As these technologies become more sophisticated, we may find that the distinction between simulated and real space-time becomes increasingly blurred. If space-time is fundamentally informational, as some theories suggest, then sufficiently advanced simulations might be indistinguishable from physical reality, not just to observers within the simulation, but in terms of their actual physical properties. Future technologies might even allow us to directly manipulate space-time itself. If space and time emerge from quantum information processing, then quantum computers might eventually be capable of creating artificial space-time geometries, generating localized regions with different physical laws, or even creating bridges between distant regions of space. The development of metamaterials, artificially structured materials with properties not found in nature, has already shown that we can manipulate electromagnetic fields in ways that seem to violate our intuitive understanding of space. Future metamaterials might allow us to manipulate gravitational fields, create artificial black holes, or generate exotic space-time geometries in laboratory settings. These technological developments are not just tools for testing existing theories. They are fundamentally changing what kinds of questions we can ask about space and time. As our ability to manipulate quantum systems, detect gravitational waves, and simulate complex physics continues to advance, we may discover aspects of space-time that no amount of theoretical speculation could have predicted. The future belongs to those who can bridge the gap between theory and experiment, using technology to probe the deepest mysteries of existence, and perhaps even to reshape the fabric of reality itself. As we stand at the frontier of human knowledge about space and time, we face questions so profound, they challenge the very foundations of existence, meaning, and our place in the cosmic story. The answers we discover in the coming decades will not just advance physics, they will transform what it means to be human in a universe far stranger and more wonderful than we ever imagined. The ultimate question haunting all of physics is this: what is the fundamental nature of reality?
Are space and time foundational features of existence, or are they emergent properties arising from something more basic? If current theories are correct, reality at its deepest level might be neither material nor spatial nor temporal, but pure information, quantum bits processing themselves into the appearance of the physical universe we experience. This informational view of reality leads to staggering implications. If consciousness is a form of information processing, and if reality itself is informational, then consciousness might not be an accidental byproduct of cosmic evolution, but a fundamental feature of existence. Whole is 4, 4, 4. We might be living in a universe that is, in some sense, intrinsically conscious, where every quantum interaction involves rudimentary forms of information processing and experience. The question of consciousness becomes even more pressing when we consider the measurement problem in quantum mechanics. If conscious observation plays a role in collapsing quantum superpositions, then consciousness might be actively participating in the creation of reality moment by moment. This would make us not just observers of the cosmic drama, but co-creators of the universe itself. But this raises the deepest question of all. Why does anything exist rather than nothing? If space and time are emergent, if matter reduces to energy, if energy reduces to information, and if information can be created and destroyed, then what prevents the universe from simply not existing? What is the source of the ultimate asymmetry between existence and non-existence? Some physicists speculate that existence might be more stable than non-existence, that nothing is actually an unstable state, that inevitably gives rise to something. In this view, the universe exists because non-existence is impossible, but this only pushes the mystery back one level. Why should the laws of logic and possibility themselves exist? The multiverse hypothesis offers another perspective. Perhaps every possible universe does exist, and the question is not why something exists rather than nothing, but why we find ourselves in this particular branch of infinite reality. If the multiverse is real, then somewhere there are versions of you reading different versions of these words, asking slightly different questions about the nature of existence. But the multiverse raises its own ultimate questions. What determines which universes exist in the multiverse? Is there a meta-universe that contains all possible multiverses? Can consciousness navigate between different branches of reality? And if so, what does this mean for personal identity and the continuity of experience? The discovery that space and time might be quantized, pixelated at the Planck scale, suggests that reality might be computational in nature. If the universe is literally computing itself into existence, then we are patterns of information within this cosmic computation. This computational view offers hope for the ultimate questions. If reality is computational, then in principle, it might be possible to understand the algorithm that generates existence itself. Advanced civilizations of the future might achieve something approaching omniscience, complete understanding of the computational processes that generate reality. They might be able to read the source code of the universe, edit the laws of physics, or even create new forms of space and time. From their perspective, the questions that seem ultimate to us might be solved problems like arithmetic is to us now. But would such knowledge bring meaning or nihilism? If we discovered that reality is just information processing, would this diminish the significance of love, beauty, consciousness, and moral purpose? Or would it reveal that these experiences are the most remarkable features of existence, the universe's greatest achievements in complexity, information integration, and self-awareness? The anthropic principle suggests that consciousness might be not just a product of cosmic evolution, but its purpose. If the universe is fine-tuned for the emergence of conscious observers, then perhaps consciousness is the meaning toward which cosmic evolution strives. It is the meaning of cosmic evolution strives. We might be the universe awakening to itself, developing the capacity for wonder, understanding, and moral choice. This leads to questions about our cosmic responsibility. If consciousness plays a fundamental role in determining reality,
then what obligations do we have as conscious beings? Should we spread consciousness throughout the universe, creating new forms of awareness and understanding? Should we preserve and protect the conscious experiences that already exist? Do we have a duty to continue the cosmic evolution of complexity and consciousness? The future of space and time research might reveal that these questions have surprising answers. We might discover that consciousness naturally spreads throughout the universe, that intelligence inevitably emerges wherever sufficient complexity develops, and that the cosmic story is fundamentally about the growth of awareness, understanding, and meaning. Or we might discover that consciousness is incredibly rare and precious, that we are among the first flickering candles of awareness in a vast cosmic darkness, bearing the profound responsibility of keeping the light of consciousness burning and perhaps spreading it to the stars. The ultimate questions about space and time are really questions about ourselves. What are we? Why are we here? What is our purpose in a universe that somehow generated the capacity to ask these questions? The answers we discover will not just satisfy our scientific curiosity. They will determine how we choose to live, what we value, and what kind of future we create for consciousness in the cosmos. As we probe deeper into the mysteries of space and time, we are not just exploring the physical universe, we are exploring the meaning of existence itself. Every measurement we make, every theory we develop, every question we ask is the universe examining itself through our minds, seeking to understand its own nature and purpose. We are the universe's way of knowing itself, and through our investigations of space and time, we are writing the next chapter in the greatest story ever told. The story of how something came from nothing, how complexity emerged from simplicity, how consciousness arose from unconsciousness, and how meaning might emerge from the vast cosmic process that brought us into being. The ultimate questions remain open, waiting for future generations to probe, answer, and transcend. But we can be certain of one thing. Whatever we discover about the nature of space and time will be far stranger, more beautiful, and more meaningful than anything we can currently imagine. So here we are, after journeying through the deepest mysteries of space and time. What have we discovered? We've learned that the stage upon which your life unfolds is not what it seems. Space is not empty. Time does not flow. The present is not universal. Reality is not predetermined. Instead, we inhabit a universe of impossible beauty and strangeness. Space and time are woven together into a dynamic fabric that bends, stretches, and vibrates with the music of existence. What we call empty space teems with quantum activity. What we experience as the flow of time emerges from processes we're only beginning to understand. We are not separate from this cosmic drama. We are patterns of information and consciousness that have emerged from the universe's evolution. We participate in the collapse of quantum possibilities into definite realities. We are the universe's way of experiencing its own existence. The questions that drove our journey remain as profound as ever. Why does anything exist rather than nothing? How does consciousness arise from unconscious matter? What is the source of time's arrow? These mysteries point towards something deeper than physics can currently grasp. But perhaps that's the point. We are meaning-making beings in a universe that has evolved the capacity for meaning. We are the cosmos awakening to itself, developing wonder, understanding, and the ability to ask why. The reality you inhabit is stranger and more wonderful than any science fiction. You are made of star stuff that has learned to contemplate the stars. You exist at the intersection of quantum possibility and cosmic evolution. You are both observer and participant in the grandest story ever told. You are both observer and participant in the grandest story ever told. What strikes you most about this journey through space and time? Or does it change how you experience this moment, knowing that you're participating in the cosmic process of creating reality itself? If this exploration has sparked your curiosity about the deepest mysteries of existence, I'm grateful we could share this intellectual adventure together. Your engagement means the universe is literally using human consciousness to better understand itself, which is perhaps the most remarkable fact of all. The cosmos has so many more secrets waiting to be discovered. Every answer reveals new questions,
every solution unveils deeper mysteries. If you're ready to continue this quest for understanding, explore our other journeys into the heart of reality, where each investigation brings us closer to comprehending the magnificent strangeness of our existence in this impossible universe.